So objective of today's class is to discuss this bioinstrumentation one paper. I feel this paper is certainly, easium. At first, it's medium. So it's just a matter of recall and applying the formulas correctly. So let's quickly go through this. I'm expecting a lot of help with formula relations and all that, because I don't tend to remember many of these relations. Let's get started. Yes. So first thing to realize, this equation is at the core of, many concepts in bioinstrumentation in biomedical engineering syllabus. Okay, this thing tau is time constant that plays a very significant role. Okay, you can apply this to equation to many places. So knowing what the solution here is going to help you a lot. Okay, and this is very simple. Let's quickly solve this. So I suppose variable separable, just two terms. So dy by d is minus dt by tau. And integrating on both sides, we have ln of y by y naught is minus t by tau. Okay, this implies y is y naught e power minus t by tau. Right? Okay, so there's a solution here, and idea is try to recognize, try to find time in any given first order system, and you essentially know its solution. So this thing has no RHS. RHS is zero, or there is no input here. Then our second thing is to know how the system behaves with an input. The standard input is, okay, we apply a step input, how does the system behave? And so that's where we need to solve. And the quickest way I suggest here would be to do Laplace transforms. Okay, if you take Laplace transform on both the sides, you have s y of s plus y of s is a over s. Okay, and now it's a matter of getting this, finding y of s and then taking inverse Laplace transform. Of course, Laplace transform can handle initial conditions. So we have tau times y of 0, that is y naught, from taking Laplace transform of the derivative. So let's also have that term over here. So we have y of s into tau s plus 1 is tau y naught plus a over s. Suppose this expression is correct, right? There are issues, just quickly let me know. And rewriting this, we have y of s is y naught by tau s plus 1. And if you bring the tau, you have s plus 1 by tau. Okay, this is convenient to take inverse Laplace transform. And this term is a by s into tau s plus 1. Okay, so it's easy to take inverse Laplace transform of this. This is a constant 1 by s plus a, we know it's e power minus at, inverse Laplace transform. So this term we have to do partial fractions. So the thing continues here. Y of s is y naught is a very convenient term. And what happens to this term? We need two terms. There is going to be a 1 over s like term, and then there's going to be a tau s plus 1 like term over here. A is a constant that came out. So if we have a tau here, the thing cancels, and we are left with a correct term, right? So this is tau s plus 1 minus s tau, that is 1 by s into tau s plus 1. And we have the a over here. And again, we are going to take this tau to a convenient location, okay? S by 1 by s plus 1 by tau. From here, we can take the inverse Laplace transform, that is y of t should be equal to y naught e power minus t over tau. And then we have a u of t, inverse Laplace of this is this, and minus e power minus t over tau. Okay, fine. So this is the solution that we have. So 2 points. First thing, yeah, typically we are interested in systems with some kind of input, some step voltage, constant force, constant strain, something like that. So this equation is again, it's also important. Okay, the behavior and solution is this, and this also illustrates how do you use Laplace transform to quickly take, to find a solution for a differential equation. Couple of things that I have used here is Laplace transform of e power minus at. Okay, this is 1 by s plus a, and then Laplace transform of u of t is 1 by s. Notice uniform function is that this a is almost it is 0 for a take an exponential function in the limit a tending to 0, the exponential doesn't drop at all, almost remains a constant, right? That is u of t. So when a is 0, you get 1 over s. Okay, so these two are fine, and quick application of that, irrespective of what things are, it can be current in an LR circuit, it can be voltage in a CR circuit, it can be given time and the corresponding y of t, and from there we can find many things. So what do we need here? Okay, who showed up right now quickly? Who was the person who showed up now? Just that we have some attendance here. So whoever that is, Vaishnavi or Dinesh, I suppose, either of you, just leave your name so that you were in the beginning of the class. Okay. So the data shown in the table above was collected for a step response of an unknown first order system. Okay. Yeah, the beauty of this is y of t can be anything, right? In GATE, they have given problems where this is from a LR circuit and so on, right? In this case, we need the time constant of the system. Okay, and here the response is relatively simpler. We have like we have y of t typically for a first order system we have a steady state response, YSS, then there is a transient response, right? And in fact, it's also possible to write this as a steady state response and the transient response. A u of t is a steady state response, and 1 minus y naught minus a, that will be the transient response, right? So having written this way, what happens is, notice wherever you start, in this case you start from 0, y of t, wherever you start, you eventually go towards a steady state value. Interestingly, here things don't change anymore. That means we have like a 2.28 kind of, we reach the steady state. Starting from 0, here we go here. So steady state value is this. When t is infinity, you get this whole term to be 0. What is left is YSS. So that is YSS. We know that. And quickly to find k, use this time, this data point, because when t is 0, this term becomes 1. So it'll be easy to handle with. Notice, so first thing, YSS is 2.28 in the given data. And second, we have y of 0 is 0 equals YSS plus k. This implies k is minus YSS, that is 2.28. From there, we have to find the time constant of the system. Yeah, there are actually shortcuts to find time constant of this system. So let's also discuss that. From here, third step, to find tau, use any one data point, or can we do it some other means? So I suppose, in the speaker, we always recognize tau is the time constant. It's the time, that is when this is tau. Okay, when t equals tau, we have y of t is YSS plus k into e power minus 1 into 1 by e, right? So the y value should be, notice 2.28 minus 2.28 by E. So what is this value? Okay, 1.44, approximately 1.44. So the point of finding this is, now you could actually do two things, right? There are many ways to find tau constant. At this, in this equation, there is right now, we know YSS, we know K, only tau is an unknown. We have so many data points. Plug any data point, we can find that. Or in other words, we can see when T is tau, Y of T should be 1.44. So it's somewhere between 1.3 and 1.54, right? Somewhere in this interval. Roughly, if you do even like, it kind of varies, but say it varies linearly. The midpoint between these two is where 1.45 is there, roughly. Okay, 1.3, 1.55. So somewhere in between these 2 points. Okay, so just by looking at this, you could guess your tau is approximately 0.17. That is just by looking at, it's a value between 0.15 and 0.2, can be more precise. Okay. If you just do linear extra interpolation, whatever, you could get the time constant, or just if you want to be careful, just use some data point, or just use some data point. Say, what do we have here? Let's pick something not to this extreme, to this extreme, somewhere convenient. Let's pick this. So we have x of t, y of t is 0.3, 1.86. Just use this data point. There is one unknown constant in this equation right now. You can find that out. Okay. Let's get to this question. Yeah, this is just to highlight what is sensitivity of a sensor. You are measuring something output. Your input is something. Change in output by change in input is sensitivity. Okay, here we want the average sensitivity. So quickly, we have like between average sensitivity between 70 to 100 degrees Celsius. We have a sensitivity here, we have a sensitivity here, we have a sensitivity here. Can we quickly have the sensitivities? The number sensitivity is delta output, okay, Q output by delta Q I. In the limit, it's a derivative of dq by output over input, but approximately it's this change. So what is the slope here? What is the slope here? What is the slope here? Let me write it for one point very clearly. 67.8 by 10. Okay. So we have 70.4 minus 67.8 divided 10. We have 0.26 millivolts per degree Celsius between 70 to 80 approximately. Okay. And what is the sensitivity at the two other points? Between 80 to 90 and 90 to 100. Okay, then we have this to be 0. I suppose this is 0.17 and we have 0.09. And what is the average of these three values? 0.09 plus 0.17 plus 0.26 divided by 3. We get roughly 0.173. This is the average of these three values. Okay, 0.26 plus 0.17 plus 0.09 by 3. Again, it just, sensitivity is a very well-known concept. You should be prepared to read it from a table like this. And ideally, sensitivity will be the slope. If it's a straight line, it will be the slope. You have to fit a straight line linear regression here, then find that constant, the slope from that equation. If you fit y is ax plus b, straight line here with this 4 data points. A will be the sensitivity. Approximately it will be 0.173. Okay. Transducer has a sensitivity of 10 microvolt per volt per gram. Okay, here we know it's a transducer. This is a passive transducer. It needs an external source. It's also needs, it's measuring something. It's typically force. So there is per volt per gram. This answer is very, very simple. V out is take the sensitivity, okay, multiply that by excitation potential into phi, and multiply that by applied force in this case. Notice this is a passive force transducer. Force transducer. So what do we get here for this? And this sensitivity is 10 into 10 power minus 3. So there is a 10 power minus 6 over there. Have that 10 into 5 into 15 to 10 power minus 6. We have 7.5 into 10 power minus 4. Okay, 7500000. So this is our answer. We want the things in volts, so our answer should be, what I get is 7.5 into 10 power minus 4. So that equals 0.00, 0.75 millivolts. But notice in GATE, we have to enter answers for the unit that is given in the question. Mostly units will be given. It's GATE level question doesn't make sense. Okay, so you need to enter this. Okay, so quickly, what is what? Left mid-clavicular, and one of the things right now, the point to giving the GATE questions is to compare and contrast the questions that we are studying with what has been already asked, and it also helps a revision. Third is, when a question like this comes, you shouldn't just know what does left mid-clavicular, fifth intercostal space corresponds to. Okay, in this case, I suppose that corresponds to mitral, and between first and second, a systolic sound, so there is regurgitation. Now, again, we have an issue here. Okay, so this is mitral, and notice between first and heart sound is systole. Right, and this is the heart tries to pump. Okay, we have the aorta here, we have the mitral valve here, and yeah, so the LV is over here. Between first and second sounds, heart tries to pump. Okay, this valve is supposed to be closed, and blood is supposed to go through aorta. But what happens is there is flow across, there is leakage through this valve. That happens during systole when the heart tries to pump. That is the first and second sounds. So this is known as regurgitation. Mitral valve. So that arrow is mitral regurgitation. Yeah. So the reason to have GATE questions in this paper is manifolds. One is compare and contrast. Okay, that is to see, okay, roughly how difficult or easy the questions that we are practicing studying with respect to GATE questions. Second is it helps with revision. Third is the most important thing. That is, there is a question like this, you just shouldn't know about, just about mitral regurgitation. You should know the corresponding cases for aortic stenosis, mitral stenosis, aortic regurgitation. If it's an MCQ question, at least you should know what the all other options are. And typically, I'll go look at PCG and say, where is different sounds heard and all. That's a reason to give this question over here. Okay. In fact, if you print it out or something like that, it also helps to leave short formula and then all the notes, then and there, so that you could also revise. Yeah, that point is also emphasized here. You can answer this question, but we are not expecting you to really answer this question. We want you to be, if a similar question shows up with EEG, okay, something else, EMG, EEG, PCG, whatever it is, you should be able to compare and contrast. Okay, have that in mind when you go through this. And for this question, I suppose they have comparable gain. And EMG certainly has a larger bandwidth. So we have B over here. Why is at least 20 dB higher gain? They both have like similar millivolts, around 0.1 millivolts, both of them, ECG and EMG. Why does surface EMG need higher gain? Okay, I suppose only B is the answer. There is no, you don't need, the gains are comparable. EEG system processes a 5 microvolt signal in the presence of 100 microvolt random noise level, unprocessed SNRS. Okay, we'll have to introduce many concepts here. There is one important detail. Let's just first answer this question. Signal to noise ratio. Okay, notice in dB, we are talking about volts, amplitudes. Right? We are not talking about powers. So this should be 20 log of V signal by V noise. Signal to noise ratio is V signal by V noise. That in decibels will be 20 log this by this. Now, so this should be pretty straightforward to calculate. We have 20 log signal amplitude is 5 into 10 power minus 6 and noise amplitude is 100 into 10 power minus 6. Okay, that makes this quickly. Okay, we have one answer, Nandini. Others 5 divided by 100 and log of answer into 20. So minus 26 dB. Be careful about the sign. It has to be minus 26 decibels. Essentially, it says noise level is actually much higher compared to what you have here. Okay, the sign is very important here. And also calculate the SNR and processing gain dB for 100 repetitions of the signal. Okay, that is, this has to do with something called signal averaging. We haven't seen this yet. Can someone quickly look at BME, Bioinstrumentation 3 paper, the second latest paper, and see if you have this question asking you to calculate the process SNR or processing gain? One of you, can you quickly check that? Signal averaging. We haven't seen the underlying theory, but I'll briefly mention that. If you have this question, there in the next subsequent paper, we'll skip it right now. Quickly, it should be there in the initial stages. It wouldn't be hidden somewhere deep beneath and all that. The idea is any signal, let's say ECG, have, right, you have ECG like this, right? Typically, this will be very, very noisy. And when you, so sometimes even details are kind of hidden in noise based on what the noise amplitude is. What you typically do is to get multiple ECGs and average the signals. This is one signal. You get lots and lots of such signals and you align them based on some discernible feature. In this case, let's say the R peaks. Okay. In this case, it says you take thousands of such signal and you take the average value. That average value, interestingly, noise is sometimes high, sometimes low. Okay. On an average, that will get cancelled. But signal is always high or low. So the process of this is signal increases and noise decreases. Okay. And based on a number of things we use, we know how much the amplitude and noise changes. Did it is there, right? Yeah, this is a slightly advanced, so I have given it there. So this is this idea of here processed SNR and processing gain for 1,000 repetitions of the signal. That means they are taking 1,000 signals, averaging that, and then that is the processing they do. Based on the processing, signal will be higher, noise will be lesser. But what is the processed SNR and processing gain? Okay, we'll come to this once we do signal averaging. Anyways, it's there in the next paper. Okay. Which of the following displacement sensors is known to have a high sensitivity and a relatively large measurement range? There are two conditions given, but we can answer this with one feature. Yeah, it's a displacement sensor. You use strain gauge to measure displacement. Strains are very low. And strain gauge nasty. Again, capacitance sensors. Not a good idea. You can't measure large displacements. Piezo, it's like again not a large measurement range. The thing that really works best is of course LVDT, and so happens that LVDT's sensitivity is also very high, so that kind of makes it stand alone. So that's an easy picking here. And so point here is ability to compare and contrast various sensors, know the pros and cons of strain gauge, capacitive sensor, piezoelectric sensor. It doesn't suffice to know what the underlying formula is, but also know, okay, in this setup, comparatively LVDT will perform better, piezo will perform better. That kind of, you should be able to compare and contrast sensors, features of sensors. In fact, that is highlighted by one more question over here. Temperature sensor used in contact type digital thermometer for measuring body temperature. We thought we will find one counter example and then we'll appeal for marks. Unfortunately, we couldn't find any counter example. The reason being, none of the companies offer a contact type digital thermometer that uses either a thermocouple RTD or an, this is for non-contact type. None of them offered a thermocouple or RTD. The point boils down to many features. One is the range of measurements. Body temperature, we are interested in a small range, and we want to be highly accurate in that range. So sensitivity should be very high, right? So this range, in fact, for the body temperature measurement, biomedical application is small, and then sensitivity is extremely high, highest for a thermistor. And then there are also some aspects like cost, life, and reliability and all that. Thermistor, semiconductor based devices usually, they outperform the other opponents over here. So no, the answer is first of all, notice this is a GATE BM 2021 question. Okay, the answer is B. It's unanimously B. There is no A and C. This, of course, is used in what is it? Non-contact type. At least you can start thinking of a setup like that. Infrared LED photodetector pair. Photodetector pair typically in a pulse oximeter, but you can always design a system to measure temperature. Okay, the answer here is B. Be careful about it. And this is also a GATE BM 2021 question. Okay. I'm surprised. Okay. This is arrangement of 4 resistors. So in pressure measurement, we have this strain gauge, Wheatstone rich configuration. Applied pressure is observed to cause an increase in length of resistors. So this statement says, we understand, let me write it. This statement says length increases, del L increases, so R2 and R4 increase. Okay, this statement, increase in cross-sectional area, that says del A increases. That means due to Poisson's effect, length decreases, and resistance typically changes, increase or decrease based on length. doesn't change based on cross-sectional area. So, or this factor is the most important, most significant factor. So R1 and R3 decrease. So that's what they mean by those two statements. The idea is we want to get the voltage proportional to the change in resistance. Notice we don't never measure change in resistances as such. We try to measure corresponding changes in voltages because changes in resistance are very, very low. We don't need another very precise resistance measurement device for separately for that, right? We can't afford to do that. So we convert that to voltage, and here the only thing is you have to put them in opposite branches so that things things are not balanced anymore. Let me say this is plus and plus, and this is minus and minus to suggest this decreases, this thing increases. You have to have the pluses and plus and opposite branches. Okay, that is if we have plus and plus here, minus and minus here, the ratio of R2 by R4 can be equal to ratio of R1 by R3. We'll get a balance possible. Okay, here balance possible. Balance is possible, we won't see any output voltage at all. So this is not the thing we want. Instead, we want things in opposite arms so that we create an imbalance that we measure. So we have plus and plus here, minus and minus here. So all you have to see is this opposite arm configuration so that it's imbalanced. And in that imbalance, output is approximately proportional to 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 the change in resistance del R. It's a very, very typical question that shows up in instrumentation papers. Okay, know this question thoroughly. So here the answer should be only this configuration will give this. So this won't give, that makes of course neither is problematic. One will do the work. Okay, this question we had some issue. So yeah, I corrected the question. Yeah, the thing is, is 0.1 meter long. So it's actually a very small elastic resistive transducer, almost like a rubber band. And I also gave you an example. Take some rubber band, coat some this pencil lead on it. You almost got a similar sensor. Just that how robust it is, reliable it is a question, but you will start noticing sufficient resistance and potential changes. So 0.1 meters. Say this was the sensor 0.1 that became it is 1 for 12 or 1.2 meters. It's actually stretched a lot, and from here breathing will change this 1.2 meter will go slightly higher or lower from here. And we have so much detail over here. Assuming normal breathing produces 10% change in circumference. So 10% change, so it could be an increase or decrease, notice. So from 1.2, things are going to change by 10%. So we always apply a current of 0.5 milliamps. So what should be the change in voltage? So voltage is I times R. Current is a constant, so change in voltage is equals, corresponds to change in resistance. Okay, there is one more statement given here. Assume that the cross-sectional area of the transducer remains unchanged. So what we have to do is we have a R naught here. We have a R stretched here. and we have a that goes to, we have a R breathing. So from the R stretched position, if we know V, we can calculate del V easily. We know the change in percentage. So del R corresponds to del L. Okay. So this also corresponds to del V. Okay. There is 10% change in length of circumference. There is going to be a 10% change in resistance. There is going to be a 10% change in voltage. Right. But in order to find that 10% voltage, we need to know what is volt. And this voltage is at V stretched. So if you know what the stretched resistance is, we can calculate what the change in voltage is. So Swarnendu, do you follow till this detail? If you know what is R stretched, we can calculate what is V stretched in the stretched position, that is in the reference position, and from the reference we can measure changes.
Yes, so now it's more clear after you have made the change.
Okay. After making the change, it's clear. And of course, what they are asking for is a change in voltage due to breathing. That means, this is breathing. Okay. So find R stretched, find voltage, then change in voltage is going to be, just 10%, because everything is linear here. This is 10%. This means this will be 10%, and this means this will also be 10%. So what we really need to find is R stretched. How do we find R stretched? That is where we need to find resistivity. So first is this R naught is rho L over A. Okay, this is L naught. From this, find what is rho. Quickly, someone in the chat. We have L naught is 0.1. Diameter doesn't matter because area changes, cross-sectional area changes doesn't affect. 12 kilo ohm. Hopefully that is okay. 0.196. This implies R stretch is rho L stretched by, again we also need we somehow we also need to use this A. Yeah, cross section remains unchanged, so this is unchanged. So what do we get for R stretched? Don't want to. Yeah, this problem is easy, so we can overspill a little. So this R stretched, I suppose, Varnendu's answer is 12 kilo ohms. Roughly does make sense. So 0.1 is 1 kilo ohm. 1.2 is multiply that by 12. Yeah, this should be, let's say, 12 kilo ohms. That implies V stretch is 0.5 into 10 power minus 3 into 12 kilo ohms. 12 into 10 power 3. So this is 6 volts. 10% change will be 0.6. Okay. And all of you are also able to see the change in the question paper right now, right? It's not like the change is reflected in your question paper, all your question papers. Okay, great. So, but yeah, this problem is just to illustrate this idea of this, resistivity. Other than that, it's not all that, realistic at all. Cross section changes and the resistivity being a constant all along. There's so many problems with it, but at least yeah, there are sensors like this. You can quickly measure, monitor breathing pattern based on this sensor. But numbers won't be that simple. Okay, let's get to question 13. Wheatstone bridge with 12 volt DC source contains the following resistance. Output voltage is V. Okay, I think we did some of these questions recently, so let's quickly glide through them. Ideally, the sign here is important. Let's say what we choose as positive terminal, what we choose as negative terminal is important. Okay, because E naught is VC minus VD. That is VC, it's simple to say. You apply 12 volts here, so that gets split between these two. Okay, this is not balanced, but yeah, that's where we get this output. So VC is all of them will be a fraction of this 12. What fraction? Voltage divider, it's R2 by R1 plus R2. So R2, R3, R4. So it is 3 by 1.2 plus 3, and VD will be R4 by R3 plus R4. So 5 by 2.2 plus 5. And this sign here determines whether this is this minus this or this minus this. So ideally this should be given, and presuming this sign we have 0.24. Simple question here. So let me leave a note on this. So this convention needs to be given, will determine sign of answer. And unless they ask for magnitude, you have to enter things with the correct sign. And this is also a feature of Wheatstone bridges. What sign you get depends on how you connect it. So this is not a question that sign is immaterial. Sign does matter from the design perspective and actually construction perspective. So they are also GATE is also pretty concerned about the sign here. Be careful there. Okay, this question, change in resistance. So we are given resistivity, we are given change in area, we are given original length, change in length, original area, change in area. So find the two resistances, and this is R del R should be this R R new minus R old. This is rho L plus del L by A. So cross sectional area decreases L minus del A. Okay, this is R new, and R old will be just rho L by A. So we have given rho is given resistivity, then L is given, and then A is given. This is del L, and then we have area decreases. Okay, and that is minus del A. Okay, so quickly, if we substitute this, what is the resistance we get? Again, we have to be also at this stage careful about final numbers 1.23. And the intermediate should be what minus what, or new minus R old. Can you also get some? So something is 1.23. This minus this. What is R new? What is R old? Just so that someone tries to, redo this, they'll have intermediate numbers. 2.73 minus 1.5. Great. Okay, then we are still in strain gauges. Yeah, they are somewhat important. 20 mm length of wire, so strain gauge exhibits the resistance. Force is applied in tension. Resistance changes by this. Length changes by this. Gauge factor. Gauge factor is simple. This is del R by R by del L by L. This is the definition, and based on this definition, there is also another 1 plus 2 nu plus, I suppose, del rho by del L by L. So I suppose gauge factor can also be found from this expression. But for today, things we need for definitions are given. So using this, we get the gauge factor to be roughly 220 divided by 2. 3.80 sounds slightly higher. Is that thing? Del R. So we have 2 into L 20 divided 150 divided 0.07. 3.8. Fine. Based on the given numbers, it's 3.8. One more question again from strain gauges, but this time we have null condition. Each element has a resistance of 200 ohms. When a force is applied, each resistance changes by 10 ohms. Output voltage if 10 volt excitation potential is applied to the bridge. So we need to say what changes and how we measure things. So in this configuration, okay, so there are many details hidden in this question. One is uh, in this config, okay, change means different things for these things. If R3 and R4 in tension, then R1 and R3 and R2 in tension, R1 and R4 in compression. So typically like the Poisson's effect. Okay. So we need to know what is in compression, what is in tension, so that one of them becomes 210 and the other two becomes 190. Right? Change is 10, but it can be increase or decrease. So let's pick something. Let's say this is compression, compression, tension, tension. And here also we have to say how this voltage is measured. Let's again go with this notion. So this is plus, this is minus. All of this will actually determine the sign of this. And for the given thing, our output voltage E naught is, let's say, this point C minus D. Okay. Or, not confused with that C, let's call it some point, G and H. So we have VG minus VH. So they are all, we can quickly find out using voltage division. There is a 10 volt excitation voltage, and here we have R2. R2 is in tension, increases, so that is 210 by 210 plus 190 minus R4. R4 is in compression by 210 plus 190. So in this case, we get a positive sign. This will be 0.5 volts. Based on what this is, and specifically the question will also mention, just like the other question, which two are in compression, which two are in tension. The sign can be plus or minus 0.5, and it's either one. And we have here sufficient detail is not there in the question. That's why I mentioned all this. For the question to be well posed, all this should be mentioned. With that, only one sign will be correct. Okay, be very careful here. That's the only detail. Okay, I think we kind of finished all the strain gauge things. So fine. Let's quickly do this. So where is this question we haven't seen so far, but it's a straightforward application of electrical circuits. So where does this fit into the syllabus?
ECG?
ECG. Any other answers? We are not really measuring. It says, okay, there are some resistances. We actually send a current. Star delta. No, which subtopic from the syllabus? This is from Yeah, this is a simple electrical circuit, but it's applied to bioinstrumentation. No, it's not ECG-led configuration. This problem doesn't have to do with ECG-led configuration. So let's focus what they are asking, the current passing through the heart. Why are they asking for the current passing through the heart? Or why are they even trying to model that? Microshocks or shock is to see if this current is sufficient enough to create ventricular fibrillation. The reason to model this and see what happens. In fact, this is actually from macro shock. So electrical safety, right, in bioinstrumentation is one of the typical numericals they could ask. Safety from bioinstrumentation. Idea is, I think there is a threshold current, depends on a lot of factors, weight of the person, and also like, the conductor size and all that. But typically there is, for standard conditions, there is a threshold of current beyond which we cannot let go of the conductor, and then we'll have some respiratory problems, and then we'll have ventricular fibrillation, at which point it gets fatal. So idea is always we want to ensure this, all the sources here, we want to limit the currents so that it's below that ventricular fibrillation limit. It's roughly, approximately 75 milliamps for standard conditions. Standard conditions will define standard conditions, but this is where the problem fits into. But how we model with that is a simple circuit. And notice along the currents path, we have we have we have this resistor. Okay, we have this resistor. The other two resistors doesn't play a role in the currents path. They are connected, but it's not connected to the circuit. So this doesn't matter, this doesn't matter, this doesn't matter, this doesn't matter. And also we, the toss also, they haven't given any finite resistance for it, but that's a model. Okay, so none of it matters, only this matters. So current passing through the heart according to this model is Vs by Ra, the resistance of the two arms, Ra plus Ra, and that is 120 by 400 plus 400, and this is 0.15 amps, that is 150 milliamps. That is actually, yeah, this current is, in fact, the question will be, according to this model, the current is sufficient enough to cause ventricular fibrillation, not sufficient to cause ventricular fibrillation, cannot be determined from the data given, and then or perhaps they have to cook up one more option. That is also possible. They can either ask for the current or make you recall some relation and thresholds for ventricular fibrillation and ask you, is it sufficient for causing ventricular fibrillation? Both the kinds of questions are possible, but at the end of the day, simple electrical circuits. Okay, so now we have some basics of capacitor, inductor, resistor. We can glide past them. We have had this discussion during admission. So yeah, we want the current test, right? So current is I is C dV by dt. So it's capacitance times the slope. 2 times the slope here at 1.2, 1.5 over here, so 1.2 over here, the same slope. The slope here is drops by 1 by a distance of 1. So slope here is minus 1 by 1, right? So the current should be minus 2. The idea is to acknowledge this formula, that is, if voltage as a function of time is given, dV by dt corresponds to the slope there, and once you know the capacitance value, you can find what the current is. This actual GATE question, yeah, 2020 paper, simple questions. So inductance is mu naught n square A over L or L over A? Quickly, anyone? It's okay, A over L. So it doesn't depend on the gauge factor at all, and it's proportional to number of turns. So there are 2 n number of turns, it will be proportional to 2n square by n square. That ratio, that should be 4. 4:1. Answer is we should enter 4. Okay, again. So in the forms, we get used to entering 4:1, 4/1, 1/4, all that. But in GATE, it's a number. Okay, you have to. It won't accept otherwise. Okay, voltage in the following circuit at time t is this. So time is anywhere between 1 and 2. So this time 1.8 is between 2 and 1. So you're looking for the slope here, which is the slope there. Again, the same thing. V is L di by dt. That is 2 times same thing, -1/1. So again, it's -2 over here. Simple question. Two metal plates with an area of 0.4 E3 cube. Okay, area is given. Separation distance is given. We have A, we have D, then we have epsilon R. They should also they should likely give, because they have been giving all the constants. So far, they haven't asked you to recall a constant, physical constant. So permittivity, free space they have given. Capacitance of the transducer, that is C is epsilon naught, epsilon R. Is it A over D or D over A? I suppose A over D, because if you make it based on distance, you don't get a, this capacitor is used to measure displacement is very, very bad because there is a defect over there. So, okay, A over D. Just plug in all the things. Okay, already in meter square, in meter, this should take care of things properly. Okay, HEMA gets, all of you get very, very small capacitance. Okay, let me also quickly do this. 0.4 into 10 power minus 3 into 2.5 into 8.85 into 10 power minus 12 divided 10 power minus 4. Okay, 8.85 into 10 power minus 11. So typically they should have given some kind of pico, nano over here. In terms of nano, this will be, this many farads. In terms of nano, this will be 0.0885 nanofarads. Or in terms of pico, it should be 88.5 picofarads. So I think this should be, the power of 10 should be properly given over here. Okay, again, in GATE, we cannot also enter a number like this. There is no provision to enter like this. So they will usually give some correction, some powers in the units they are expecting the answer. So that at the end of the day, you have to enter a proper, number. So one of you had a question here, right? Today, you sent me in the chat, what is the answer here, right? Like also, is this permittivity constant correct? Can one of you quickly verify whether what is this permittivity is?
Sir, I had a doubt. That was a bit different question. Similar concept, but a bit different question.
Okay, different question. Fine. So, yeah, but notice in the GATE, they are unlikely to ask question as simple as this. What they will do is to mix and match this with one of the other questions. So capacitance, you can match that to a PZT, and then that is tied to transducer resonance, transducer resonant frequency. Okay, they will typically make this match. Okay, this is in, of course, in ultrasound. That would be gate level, or again capacitance to PZT. They could ask for some kind of corner frequency, not resonant frequency. For as a first order system, what is the corner frequency? Okay, those two types of modifications are typically possible here, and that's what we also expect in gate, not something as straightforward as this. Okay, yeah, this is a starting point. Again, we are at a zeroth order system, calculating voltage across a piezoelectric transducer that has a thickness D, area A, and applied force F. Further, charge induced piezoelectric material is proportional to force, proportional to constant is K. So voltage is, definition of a capacitance. Q is CV, so del V is del Q. Then del Q we know is Kf, and C we know is epsilon naught or A by D. So the factor of K is missing there. So this should be A, B, C. Okay, correct. This is some topic that we haven't seen so far, but um, again, we are not, things are not hard yet. First thing to recognize, what is half cell potential. So, batteries are made up of two electrodes. There is like a cathode and there is an anode. Whether something plays the role of an anode or a cathode depends on what it is matched up against. Okay, whether Bangladesh will win that T20 match will depend on whether it's playing against India or playing against Namibia or like that's Oman, right? So same thing happens with metals. What they are matched up with is actually what determines whether it will behave like a cathode or an anode. And each metal is, um, each electrode itself is given a voltage with reference to a standard reference. So hydrogen electrode, how that behaves is set, arbitrarily it's chosen as 0. So what will some other electrode do with respect to hydrogen? Say put silver with respect to a hydrogen electrode. How does silver behave? Silver behaves as if it has a positive voltage of 0.799. So this will be the positive side. Hydrogen will play the negative electrode. Okay, if you put iron next to hydrogen, interestingly, iron plays the role of a negative electrode. So it has a negative voltage. That is, what is the direction of flow of current that says what is positive and negative, right? So we have a circuit like this. We have, typically we have a voltage like this. We have, let's also have some resistance. We have current flowing this way, right? So here with respect to hydrogen electrode, okay, let's compare that with Ag electrode. You place this, current is going to flow like this in the electrolyte solution. On the other hand, so this behaves like the positive electrode. It's given specific names, anode, cathode, and all that. We'll come to that later, but that's what these cells mean. And if you to compare this, if you place iron next to hydrogen electrode, current will flow this way. So iron will behave like a negative electrode. So those potentials are also given here because this electrolyte will have a finite resistance. That based on that we can also calculate, based on the current flow we can calculate what the potentials are. Those are the potentials given over here. And from half cell potentials, now if you put two next to each other, we can calculate the the potential of that electrochemical cell. For example, here we have silver and aluminum. You put silver next to aluminum. No, these are actually in a beaker with an electrolyte solution. So this is like we have an electrolyte solution. Imagine that setup. And we have silver and aluminum. So silver will behave like a positive electrode, and with respect to hydrogen, it has 0.79. Okay, so with respect to Al, it will have minus Al's aluminum's potential. So the total difference between Ag and Al will be, so notice hydrogen is here, or let me illustrate it here. So the total difference between Ag and Al will be this. Okay, there are two chunks there. This chunk, that is 1.706, and this chunk, that is 0.79. So the total height difference will be the sum of these two, and that is given by this. So that will be the voltage across this electrode. And if you know some kind of resistance, equivalent resistance of this electrolyte solution is 2K, we can also find the current. So current will be voltage by R. So this by 2K. What do we get? Again in milliamps, so we can forget this K quickly. What is the value here? 1.25. Again, this is a very, very basic question from electrochemical sensors. So doesn't really need any prior knowledge. And this is also the starting point of more advanced analysis. Now, this off-cell potentials plays a lot of significance. Now, our bodily fluids are like an electrolytic solution, right? It has ions, all of that you need to form an electrolyte. So you are designing a implant, hip implant, knee implant, made use of two different metals that comes into contact through bodily fluids. They are in close contact. At least almost this electrochemical cell setup you have in the body, that means there is going to be flow of ions between the two electrodes. That means the electrodes are going to corrode. That means the implant will fail over the long time. So because of that, this is specifically important concept in BME. And also many sensors to measure things like oxygen, oxygen, nitrogen, carbon dioxide are typically made using some kind of electrode cells like this, where oxygen, hydrogen will preferentially react with one metal or the other. That preferential reaction can be converted to a change in voltage or correlated to a change in voltage. So again, in electrochemical sensors also this is useful. Anyways, we'll come to that. This problem is pretty simple. Okay, so we have some thermal sensors. Quickly, simple list. Thermistor with a material constant beta. Okay, assume that the resistance of the thermistor at body temperature is this 85. Resistance of the thermistor at this temperature. So we have RT is R naught e power. So this is exponential of minus 1 by, it is, what is the formula over here?
Beta into 1 upon T minus 1 upon T0.
Okay. Beta into 1 upon T minus 1 upon T0. Okay, so I think I said you have a minus beta here and have 1 over T naught here, right? So anyways, I suppose this is correct. So quickly we have the, so notice beta is in Kelvin, this is in Celsius. So you have to convert this to Kelvin. So 37 degree Celsius is 37 plus 273 Kelvin. Similarly, 25 degrees Celsius is 25 plus 273 Kelvin. That is what you should use because we have beta in Kelvin, so that these two units cancel each other and this exponent, the power term is non-dimensional. and we have, let's say this is T, and then we have T naught, and we have R naught. So if you plug this in quickly, what do you get? 152.5. Others, I think many of you have like some kind of intern work, some many other details. Okay, 152.5. And the only thing you have to be careful about is this expression, the order of things. Find some means to remember the order correctly. Okay, then thermocouple, these are known as this empirical coefficients. Strictly, they should give a lot more detail here. The voltage seen across a thermocouple in millivolts is C naught plus C1T. It's a polynomial, and those coefficients are so and so and so on. So we stop at 3 coefficients. That is a quadratic term. This is this. So our sensitivity is rate of change of E by rate of change of T. This is C naught plus, so C naught is a constant that will disappear, C1 plus 2 times C2T. This will be in millivolt per degree Celsius. So we know C1, we know T, we know C2. Can we calculate what is S? We also want that in microvolts. I suppose this number is very small. What is this in millivolt per degree Celsius? So just find this expression over here, and that should be in millivolts per degree Celsius. We have to convert that into microvolts per Celsius. 0.0575 microvolt per degree Celsius. That should be 57.5, sorry, millivolt per degree Celsius. That is microvolts per degree Celsius. Did you get that?
Sir, in this, why we calculated E?
So
Seebeck coefficient is equal to, sir, C1 plus 2 C2 T, right, sir? So C1 given, C2 given, and T given. So why we calculate E?
oh no, this comes from this. We didn't calculate E. Sensitivity comes from this. There is a definition of this empirical coefficients is there in this relation. That is, applied voltage is quadratic in temperature.
Okay, sir.
Okay. Empirical, these constants are, you do curve fitting, find the constants empirically. That's what they mean by empirical coefficients. And if you have more constants, it's, you have like higher order terms. Here they stop at quadratic. So given the potential based on temperature is this relation, sensitivity is derivative of output with respect to input. So output potential with respect to temperature. That is C1 plus 2 C2T. That is how we get this formula. You get it from this.
Okay, sir.
Okay. And then we plug in the numbers and get this. And ideally, to actually, this relation should be given. Because, someone might write C2 plus C1T plus C0T square. That might be their convention. So technically, this star should be given. Given in question. to make sense of all these coefficients. What does this coefficient mean? Yeah, you're trying to fit that curve. In that curve, these coefficients are this. Okay. Consider a local concentration of. Yeah, someone asked me what is flux, right? Flux, particle flux. What is that flux? So it's number of particles. So some powers of 10. E8 is notice scientific notation. It's 10 power 8. So number of particles per unit area per time. So things are all moving. Say cars are all moving. Now cars don't move in two-dimensional area. Some you have a window. You have like some kind of molecules moving in and out of the window. Per unit area, per unit interval of time, how many things move? That is flux. Okay. So simple example over here to illustrate that sufficiently. So you have concentration at some region. Concentration at some region is 1E6. That is, this many number of particles are there per unit volume. Slightly 1 centimeter apart, you have concentration drops by small amount. So concentration there is drops by 10%. So drops by 0.9 E6. That will be the concentration at a 1 meter, 1 centimeter distance away. Concentration there is slightly lesser. Now, assuming diffusivity is given, flux equals 1. The diffusivity, the reason that is given as our flux, typically this goes by the term J, okay, is minus dou C by dou X. Change in concentration, that is gradient of concentration, that is change in concentration by change in length. Okay, so that is minus D diffusion is 1 e power 3. 1 into 10 power 3 centimeter square per. All these units will have, we have this centimeter square per second here. So they will properly match out. You don't have to worry about them. This is in centimeters, this is in centimeters, distance in centimeters. So no conversions required. Answer is in centimeter square. And dC by Cx will be approximately 1 E6 minus 0.9 E6. That is change in concentration. The gradient will be over the distance in which it changes, 1 centimeter. Okay. So that is minus 10 cube. Notice this number, I suppose, is negative minus. Okay, change here should be, technically speaking, this. I will explain this better today. We already tried this once, but I think I can explain this today. This change is 0.1 minus 1 E6. Okay, so that the flux is positive. It goes from higher to lower. Yeah, plus 100. I'll explain why that thing happens, why it is negative here, and I'll explain the sign convention in a why. So this is minus 10 power 5 by 1. So 10 power 5, 10 power, I get 10 power 8. Is that correct? Did I miss any term over here? This is 10 power 8.
Distance is 1 centimeter. So in the denominator, it will be 10 to the power minus 2.
No. So hold on a second. See, diffusion coefficient is in centimeter square per second. Concentration is 1 over centimeter cube, right? Units per volume. Then dx, that corresponds to 1 by centimeter. So overall, this corresponds to units per centimeter square per second. Total number per unit area per unit time. So you don't do that unit change there. So yeah, slightly be careful about it. So yeah, this is in notice units per centimeter square per second. So per unit area per unit time. So the answer here should be +1. Okay, so we have X here, we have concentration here. Let's say concentration is higher here, concentration is lower here. Okay, is gradient. So which direction should flux be? Should flux be this way or this way? Is it 1 or 2? Should it move from higher to lower or lower to higher? See, obviously, so things moving from lower to higher, why is there even some kind of confusion? It's always like you take a cup of water, you put some salt into it. Salt, the cubes that you put in are like very high concentration. Water is like distilled water, nice water. After some time, it kind of dissolves and the water becomes salty. So from higher to lower, it moves, right? So this is diffusion. You don't even have to stir, just that there is a concentration difference, things will move, right? So this doesn't make sense. So case 2 doesn't make sense. What will happen is flux will be towards the right. For the situation shown, that is concentration is higher here, lower here, flux will be along this direction. All of you agree with that?
Yes, sir.
And here is the gradient positive or negative for what I have shown here? Is the slope positive or negative? Slope is, come on, slope is negative, right? So we have J, we have dou C by dou X or the slope, okay? This we know is, say right hand side is positive, dou C by dou X is negative. So how should we relate, this and this? We add an additional negative here. So flux is along negative of the gradient, so that this negative cancels, resulting in the flux being a positive term. Simple 1D example illustrates, first of all, yeah, direction of flux should be this. It should be along negative of the gradient. So flux is proportional to negative of the gradient, that is negative of dou C by dou X. And we get this proportionality constant as this diffusion coefficient. And so at this point, you might also, some of you might wonder why we did this minus this, simple thing. So let's slightly say at x equal to 0, it is 1e6. At x is 1, it is this point is 0.9e6. Okay, what is dou C by dou X approximately? Dou C by dou X approximately is that is C2 minus C1 by X2 minus X1, or C1 minus C2 by X1 minus X2. Notice X1 is 0, so you do this. Okay, quickly questions here. So first of all, what is flux? It's a number of things that move per unit area per unit time. So that if you know what happens per unit time, you can calculate for, okay, over a length of interval, how many particles move. That calculation you could do. If you know per unit area, given the the window or area in which things move, we can also calculate again how many things actually move over a given geometry. And we have J is proportional to negative of gradient, because J is along, yeah, exactly along negative gradient. So we have minus dou C by dou X. Proportionality constant is T. Okay, any questions? Raise it. Else we'll go to the next one. Giant's good axon has a diameter of this. Yeah, this is, I think, a very straightforward question. So many simple questions again to say what is electric field. This is potential over unit length, change in potential over unit length. So many of these details are irrelevant. What is the, we want the electric field intensity, that is, so what is the potential? Transmembrane potential is 70 into 10 power minus 3. What is the separation distance? Membrane thickness, this is a separation distance T. So that is 7.5 into 10 power minus 9. So this answer should be in volt per meter. What do we get for that? Suppose the intensities are somewhat really high. $9.33 million. So that corresponds to 9.33 into 10 power 6. 10 power 6. So 9.33 megawatt per meter. Just to highlight again, just like capacitance, resistance, and all that, what is electric field? To highlight that, we have this question. Okay, fine. Intracellular concentration of group of cells averages is this. Okay, intracellular is this potassium. Extracellular potassium is this. It's here. One book refers to as the diffusion potential. The proper term for that is the Nernst potential, and this is not the membrane potential. Okay, because just one ion is allowed to move, that is known as the Nernst potential. Some rules of thumb work. Okay, Ek, that is, let's say potential is Ek is minus RT over NF ln of Ci over Co. If you have minus here, it's Ci over Co. Typically, RT and F should be given in question. RT and F, the gas constant, Faraday constant, temperature should be given. Okay, but even if they are not given, approximately we know this is at room temperature. N is 1, potassium K plus N is 1 for potassium. So RT over F, okay, it's approximately 26.7 millivolts. So just use that value and find this thing. So you have Ek is 26.7. Answers will be in millivolts, ln of CO over this. So we have 6 by 150. And answer will be in millivolts. I took the minus inside it here, so we have this. So quickly, what is that? 6 divided 150, ln of answer into 6.7 minus 85.9. Yeah, some relation that it's always easy to remember, and stick to one convention. Don't get go back and forth between ln and log here. Always use natural logarithm. Okay, because the constant will be different if you use log. Okay, one more question here. This is the proper membrane potential. Equilibrium resting, in this case, the resting membrane potential, right? Because we consider all three major ions, sodium, potassium, chlorine, and we have to use the Goldman equation. Okay, recall based, I'm not going to give that. So the permeabilities matter, intracellular, extracellular matters. So can someone quickly say what the final answer here is? And be careful. So the temperature given is 20 degrees Celsius. It's not 20 degrees Celsius is sometimes 25 is room temperature. So there will be minor changes in voltages based on how you calculate this. So anyone has, again, simple thing would be to do 26.7 approximately, okay, 26.7 ln of, we have, you should, again, the same thing, I suppose, the extracellular, intracellular, right? So Pk, then K plus, this should be, we have plus, let's say minus here, this is I intracellular, plus 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 so on. And remember, we'll have chlorine, the negative ions, things will change. So PCl into chlorine minus, this is extracellular E, and here we'll have Pk, K plus extracellular plus PNA, Na plus extracellular plus PCl, Cl minus intracellular. So what do we get for this? Is also minus 85 point, approximately that, right? Suppose you also get somewhere around this. Frog skeletal muscle, this is, I think, yeah, same data from frog skeletal muscle. Okay, let's do this life energy power rate and we'll stop there. Then rest of the questions we'll deal with in the second part of the video. Energy stored in a capacitor is charged to a potential of, that is very, very simple, half CV square. So half into 16 into 10 power minus 9 into V square. So 5000 into 5000. So I suppose 200 joules. This as such is not all that, but this can be intermediate step in important problems here. I think there is one more example, 2 or 3 problems down the line. So this is a GATE BM 2021. GATE BM 2021. Okay. So let's quickly, that is one cycle, how many ampere second takes, then how many such seconds in this, in the battery, and finally calculate, so how many years will the battery last. So very, very, very quick, let's do things quickly. Voltage is this, as a resistance is given. So in one pulse, so pulse is like this. So we have a pulse here, pulse here. We have 1 millisecond pulse for every 1 second. Okay. So 1 second essentially consumes, so 1 pulse corresponds to 1 second, corresponds to how many ampere second, how many charge, that should be 1.5 or 150, right? This is the current, and current second should be into 10 power minus 3 ampere second. So 1 second will correspond to this much amount of, charge. The battery has this many amounts of charge. So number of seconds is 2.4 ampere hour. So that is 1 hour is 3600 seconds by this whole number, 1.5 into 10 power minus 3 into 150. So total number of seconds, the year, the thing will last is this many number of seconds. And to convert that into year, divide by, I suppose, 1 year is 365 days, 1 day is 24 hours, 1 hour is 3600 seconds. I suppose, yeah, this is correct. What should you get here if you do that quickly? So this cancels 2.4 into 150 divided 15 divided 10 power minus 3 divided 365 divided 24. I seem to have missed a factor somewhere. Yeah, this is 1.5. 27.4 years. Because 2 to 3 years for a battery life is too less if you want to put a implantable device. So 27.4 makes sense. So this is an important problem. I have said this already. Some kind of life calculation, expected life calculation for a pacemaker, battery, energy calculation. You could always expect that. It's also practically very relevant from a, okay, you're making an implantable pacemaker. How much battery capacity should it have? Okay, thermistor assume self-heating voltage. The dissipation coefficient is, its unit is in millivolts per degree Celsius. That is DC. During self-heating, amount of power required to raise temperature by 1 degree Celsius. Okay, power required to raise T by 1 degrees. That is known as dissipation coefficient. At the end of the day, it's a thermistor. It's a resistive element. The moment any current flows through it, it's going to get heated up. So about what is the power required to heat it up by 1 degree Celsius? That is dissipation coefficient. And from here we have to calculate self-heating. Okay, temperature change is less than 1 degree Celsius. Voltage is this. We have to find thermistor resistance. Okay. So delta T into DC should be the power. This is a kind of question, even if you don't understand what dissipation coefficient is. Details, remember, play with units. Okay, recall just power at the end of the day is temperature delta T times DC, and then power is V square by R. Okay, so we have R should be V square by delta T into DC. V is given, delta T is given, and DC is given. So we have 5 square by 0.1 times 2 into 10 power minus 3. So what is the ohms corresponding to that? Have everything in standard so that you get ohms. Quickly, what is the value here? Okay, 125 kilo ohms. And notice So the answer here is 125 kilo ohms. Thermistor resistance. Sometimes thermistor resistances, thermistors, not all values are available. So if they tell you, give you a catalog, tell you resistance 125 is available, 100 is available, 150 is available, 250, 500 is available, you can pick a minimum thermistor based on that. Because say 100 is available, the next available value is say 250, answer here will be 250. But here just calculate the thermistor resistance should be 150. Okay? All values are available. See check catalog. See check catalog. But other than that, this step is just, even if you did not know what is dissipation coefficient, this is by this time you should have recognized it is like specific heat capacity. How much heat energy do we need to raise temperature by 1 degree Celsius? Same idea, but for a very specific process. How much power do we need to raise temperature by 1 degree Celsius? So that, based on the power, you can say, okay, the temperature due to self-heating itself, it's going to change temperature by this. Then we can measure things properly, right? And always you can use unit matching. Even if you did not know things, you can try to match units and try to solve the problem, right? This question illustrates that. Okay, simplified form of defibrillator consists of DC voltage source, charges a capacitor through a series resistor sufficiently high to store enough chest electrode. Okay. 300 joules. Size of the capacitor should be used as. So assume that the voltage to which the capacitor is charged is 2940 volts. The energy is this much. Then E is half C V square. We are given voltage, we are given E, we have to find C. So quickly, C is 2E by V square. What is that? I think 2 more problems we should do. It's an interesting example. Perhaps you can, it'll go till 35. So capacitor is charged to a voltage of 2940, and then its energy is 300 joules. So capacitance is just that. Very, very simple question. This question can be complicated, but that should be in the second version of this paper. 69.4 microfarads. Okay. Pulse generator is this, microfarads. Great. So artificial pacing, energy delivered shouldn't, again, there is a limit on energy. Okay. Energy is power into time, that is V square, V square by R or I square R is power into time. That is limited to be 300 into 10 power minus 6. So based on that, this is a different question. That is a different question. This is a different question. This is a different question. Okay. What is T? I suppose R is given, I is given, R is given, then E is given. Then we have to find T. That's, I suppose, 60 microseconds. Okay. Yeah, the powers of 10 will always be given here so that you can enter simple number. Kinetic energy term for measurement of pressure in the descending aorta is dash mmHg. Dash mmHg is the units in mmHg. Okay, yeah, mmHg for pressure plus half rho V square plus rho GH, right? So notice in Bernoulli's term, we write half rho V square plus rho GH, right? Each of them acts like an energy term. with units of pressure, right? So the kinetic energy term corresponds to this term with units of mmHg. Okay. So this is Ke term. It's an energy-like term. It's not really energy because it has units of pressure, but that corresponds to half. So we know V, we know rho. So half into 1060 into 1.5 square. How much is this? And this should be in, notice this should be in Pascal, and we should also convert that into mmHg. So what is this? Then 60 into 1.5 square divided by 2, 1192.5 pascals. So that corresponds to 1192.5 by Pascal to mmHg, you do by 133.3, 3.3, so you get 8.94. So two conceptual questions, and we'll stop the discussion. We'll not go long. So first thing, kinetic energy term for measurement of pressure in human descending aorta. So you're trying to measure pressure, and this kinetic energy term is 8.94 mmHg. So is this high? Should we be bothered about this kinetic energy, or should we presume that it's not there? That is where it boils down to. I mean, for a problem perspective, this is a number we are interested in, but is this number too high, low? Should we account for kinetic energy properly while measuring or not? That is where the actual question is. In fact, what is the drop from top of the aorta to the the aortic branch? That is another question. So what is rho GH change there? Is this term very high or low? Can this be neglected or not? Is this high or low? Okay, that is, can this be neglected? Okay, that's a reason to ask this. When we model for this, can this be neglected? In fact, that is first question. Then we should also check what is typical distance between the top of the aorta and bottom of the aorta. Can H be neglected? Also find its value, and you can answer based on that. Okay. The thing is, what we are measuring is 120 mm by 10 mm Hg is like it's almost 10% of what we are measuring, systolic diastolic pressure. So this is something that you can't neglect. Okay, this is certainly high for any measurement device. This term needs to be properly accounted for. That is the conclusion here. And here, this is, it's a nice device. Go check about what an intra-aortic balloon pump is. Yeah, what follows is also pressure, so kind of matches. Go check about this. Intact cardiovascular devices is somehow lessens the load of the heart. Now, when the heart is pumping, this acts like a suction device. So this has a negative pressure. So heart is pumping against a easier thing. So heart is trying to push, this trying to pull. When heart is relaxing, this will pump blood the other way around, not towards heart, towards the body. So it's used to relieve pressure from the heart, and based on that, in fact, some calculations based on that. You need to know one thing. Work done as P, pressure times volume, PV, right? P dV. You typically assume pressure is a constant, so you'll get P into stroke volume of stroke. Okay, and sometimes you don't get stroke volume from that. What you get as cardiac output, and that cardiac output is heart rate times stroke volume. So stroke volume is cardiac output by HR. Okay, so this is the work done, and from this you can easily calculate this. Only one detail here, this assumes P is constant, and that P typically is P systolic. P systolic, okay? Sys, P sys is constant. Okay, go check about this device, and we'll also look at not just intra-aortic balloon pump. We'll also look at, if you put a pump, what are the ways in which we can put pumps? There is no one way. There are multiple ways. Each has its pros and cons. Why would okay, intra-aortic balloon pump? The thing is, pros would be that you can put that balloon, enter the aorta through a femoral artery, easily enter, and the balloon can be compressed and easily put through a catheter, right? A percutaneous intervention, that is possible for the aorta. On the other hand, if you want to install a pump, typically you have to do surgery and all that. So, but balloon sometimes starts leaking. So there are difficulties using this for a long time. So for a short time, quick emergency, you can insert the balloon and remove the load of the heart. That works very well in that case. And yeah, read about this, and rest of the questions will continue. This starting from 36 will continue on part 2 of this video. This is part 2 of discussion of bioinstrumentation paper. And yeah, this is a relatively easy medium paper. Okay, and paper is chosen such that you don't need a lot of prior information to answer this. So knowledge mostly concerning bioinstrumentation is here. Okay, and we have already solved like half of the question paper. Today we'll solve the rest of the paper in about 2 hours or so. Okay, so for some problems it might be slightly time consuming, so let's start doing this pretty quick. Okay, I think we are here. Intra-aortic balloon pump device is applied to a patient in cardiovascular shock. The patient's blood pressure is so-and-so. Patient's cardiac output has been determined to be this. Once the balloon assist device has been started, patient's systolic pressure. Yeah, balloon assist device, one simple way to think about it is it's like, suction device. So instead of the heart pumping, there is a balloon that is actually sucking blood, into the body. So a device like that. So ultimately, what is shown here is that initially the patient's blood pressure was this, cardiac output is this. So cardiac output is too low. Idea is, can you somehow improve the cardiac output using an assist device? And once you put the assist device, you notice 2 changes. So kind of takes a load off the heart, right? And let's also see if the cardiac output has increased. Okay, with that we already saw that work done is pressure times volume, ideally, and you assume pressure is a constant, and so it becomes P times stroke volume. Systolic pressure, presumably a constant, times stroke volume, and stroke volume can be written as cardiac output by HR. I think so. What is given here is the systolic pressure is given, pieces. Then we have, yeah, number is out of range. We might be having issue. Okay, this question, right? Yeah, the thing is somehow the old file doesn't work, so let's just continue at this one. So I think everything is given. So right now work done as P systolic times the stroke volume. So that's also equal to P sys times cardiac output by heart rate. Okay, so heart rate is given, and then P systolic is given. We want to find cardiac output. Okay, cardiac output remains the same. So just find the work done. So this should be in this case equals to 65 mmHg. So answer will be in mmHg. And the cardiac output is 2.5 liters. 2.5 liters by per minute, and so the units will get properly matched. And then heart rate is 80 beats per minute. So by 80. Quickly, what do we get for this? And let's not using the gate calculator. Let's not use the normal calculators anymore. Quickly, for me this is convenient, so no, I don't have to toggle screens and all that. 2.03. I hope that is okay. So a couple of you have this 2.03 mmHg per liters per minute. Fine. See, again, the right thing to do here would be to actually go check what the work done is, after balloon pump is installed, right? So someone says if units don't match, then I mean, if it's per beat, we have to convert that to per beat. It does so much. So per minute, I think multiply by number of beats, you'll get that right. So rather, okay, if this is just this, let me also get the units correct here. So whatever I have written here, units is mmHg into liter per minute, and then we have this in 80 bpm, so that is beats per minute. Okay, so work done, so per beat is 2.03, so we want per minute, so multiply by number of beats. So 2.03 into, I suppose, number of beats is 80. Yeah, depending on what the unit is, the thing changes. Okay, so 2.03 notice is in mmHg, liters per beats. So number of beats, I think you should get this. This should be approximately 160.0. I mean, this time is 80 is just 160.06, right? Why do we have 162.5? I suppose there are two approximations going on. Okay, fine. So then this is approximately correct, 2.03. Okay, so whatever this number is, just multiply by that. So let me write down the final answer here. It should be 162.5 mmHg liters per minute. Who is that? Is Jiva right? Okay. Okay. So see, the real problem here is, to understand actually what's going on. First is find actually the work done before the assist device was installed. Find that work done. Then find the work done after the assist device is installed. Okay, this should be drastically lesser. That is the first point. And second thing is, over time the cardiac output should improve, and systolic pressure should also both should together improve because of the assist device. That is something that could be seen given more data. But I think, yeah, Webster discusses that with uh, simple case study. Okay, some very, very basic questions. Let's quickly rush through them. Small coin has a diameter of 1 centimeter, a mass of 15 grams. Pressure of this coin is just lying horizontally on a flat table. Is just okay. What this is, things in Pascal, so everything in standard unit should be the answer. 1.5. Notice the standard is kilograms, so 10 power minus 3 into 9.8. This is the weight. Okay, this is mass, this is weight, and that by area. Area should be pi into 1 centimeter square. So that is 10 power minus 4 meter square. And this should be directly in pascals. And what do we get here? Yeah, pressure is just force by area, right? Just be careful about the units and notice for the standard units for this is kilograms. So 1.5 into 10 power minus 3 kg. What do we have?
So into 4 would be there.
Into?
So pi d square by 4, no? So that 4 will also come.
Oh, area pi d square by 4. Fine. So by 4. Fine. Thanks. How many pascals is this? .87. I get something somewhat different. 1.7. 1.872 pascals. Is the book answer somewhat different? Nandini is getting 1871, 1.872. Where is this? Just give me 1 second. Into 9.8 divided 3.14 into 4. Oh, yeah, into 10 power minus 1. So why were we getting different answer now? Initially 187.3 or something like that. Approximately 187.2. Because perhaps of this 4, I suppose. Okay. So idea is gram is not the standard unit. Kilogram is the standard unit. And the moment you convert to kilogram, you should get answers in pascals. Right? Pascal should be Newton per meter square. Okay. During these questions or gate questions are there for completion's sake. During a non-invasive blood pressure measurement, arterial MAP is this. MAP is 100. That's actually systolic is thirds. Systolic is 1/3 systolic plus 2/3 P diastolic. This implies P diastolic should be 150 by 2, I suppose 75 mmHg. Okay. Yeah, pretty straightforward. When the valve is closed, as shown, the mercury in a manometer rises to a height of 120 mmHg. The absolute pressure is. So the only thing to notice is many times, so we have this gauge pressure. Okay, and then we have absolute pressure. Okay, the reference in gauge pressure is, this is local atmospheric reference. Atmospheric pressure. So if at sea level it has 760 mmHg, reference is 760 mmHg. At a different place, the pressure is somewhat higher or lower. The thing has a, the reference changes, but the gauge, the relative thing remains the same. Okay. Often one is interested in this, changes differences in pressure. So no one is concerned about absolute pressure. Typically, we are concerned about gauge pressure. And this local reference is determined by how you actually measure. Most manometers, in this case, for example, fortunately, valve is closed. Here we'll, whatever pressure is here, this rises to 120 mmHg, right? So this 120 mmHg is the gauge pressure. Because as the fluid rises here, there is an additional atmospheric pressure acting on top of it. So this pressure actually equals 120 plus 760. Okay, there is a pressure here. Because of that, this thing rises. Okay, but the total pressure at this level will be atmospheric pressure plus 120 mmHg. Okay, so this is gauge pressure. So this total pressure, absolute pressure, will be 120 plus atmospheric pressure, PATM. Typically, this is 760. So we'll have 120 plus 760, that is 88. And gauge pressure is what most devices measure and uses local reference. So reference will change based on place. And how this affects respiratory physiology, you'll have to deal with that separately. Somewhat, more involved. Okay, more easy pickings. Cardiac output of a patient whose heart rate is 90 beats per minute and stroke volume is 80 ml per beat. Yeah, I mean, CVO is stroke volume times heart rate. So volume per beat into number of beats. So that should give you this thing. So I think just get them into proper units. So 80 into 10 power minus 3 liters per bit, and that into 90 beats per minute. So just have this, we should have be fine. Suppose 8972, then we have 7.2 liters per minute. Very easy question. Patient has a stroke volume of, the idea is to gradually increase things so that you understand what is cardiac output, then how to measure it from a couple of things. Patient has a stroke volume of 75 ml. Heart rate is ECG. Heart rate is given by ECG, which in which 10 RBs occurred in 6.4 seconds. This means 9 beats in 6.4 seconds. Okay. So again, the same thing. So cardiac output is stroke volume times HR, and stroke volume is 75. We want answers in YAML, so this is 75. So one heartbeat is 1 beat corresponds to how many seconds? 9 by 6.4, right? That is approximately 1.41 seconds. So 1.4, 1 beat takes this many seconds. So per beat, how many heart rate would be length of 1 beat? That will be 1 by 1.41. This is length of 1 beat, and to convert that into minutes, I suppose you multiply by 60. This is conversion correct? So this should be in beats per minute. Or is it 60
So
into
1 beat would be 6.4 by 9, no?
6 by
6.4 by 9. The reciprocal of this.
yeah. Then I think what I calculated, you just directly multiply that. So this is 6.4, that 9 beats. So 1 bit will be by 9. Okay. This is length of 1 beat per second. Yeah, 0.71 seconds. So in 1 second, how many beats? That will be 1 by 0.71 beats. And that times, in 1 minute, this time 60 will be number of beats per minute. Okay, so heart rate is quickly 60 by 0.71. So that is 84 BPM. Once you have 84 BPM, so this into 84 is, keep things as such, roughly, let me say approximately 6,300. 6,300 ml per minute. Thanks. Okay, blood vessel has an average radius of this, length of this. If a blood pressure is this, at an average viscosity of dynes per centimeter square. Again, the point is just to highlight one detail here, that is, viscosity often is given in some interesting units. So, thing is always go with standard, convert them into standard units. So we want blood flow rate. So I suppose P is RQ. This is 8 mu L by pi R power 4 into Q. So Q is P into pi r power 4 by 8 mu. This is correct, right? I'm writing this from my memory, and let's just quickly write down what is what. Okay, thanks. So pressure is 7.2 mmHg. Convert that to pascals, Newton per meter square. So I suppose by 133 or into 133? By 133, I suppose. Into or by? Into 133 pascals. Okay, so we have pressure unit properly converted. Radius will be 0.5 into 10 power minus 3. And then length, L is also here. L is 20 into 10 power minus 3. And then viscosity, we have to do slightly proper conversion. Viscosity will be 0.01 dynes per second. So 1 dyne, I suppose, is 0.01 10 power minus 5 newtons. Dyne second per centimeter square. Right. So, okay, Samson says it's 0.001. I presume that is correct. Okay, thanks. 0.001 pascals. Just in this, the conversion unit is, I suppose, 1 dyne is 10 power minus 5 newtons. Okay. Then centimeters, there is a, yeah, I suppose the units kind of work out. So Pascal seconds. If you plug all this, you should get flow rate in liters per second. And what is that? Or you should get this in meter cube per second. You have to convert that into, that is 1000 liters per second. So just find flow rate using the values that I have written. What do you get in, say, meter cube per second or in liters per second? What do you get? And then finally, we have to convert that into ml per second. Issue's answer is that let me also quickly do this. 33 into 3.14 into 0.5. 3, 2. Mm, 1. I get 1.17 into 10 power minus 5 meter cube per second. Okay, that is 1.17 into 10 power minus 2 liters. So 1 meter cube is 1000 liters. 1000 liters per second. So 11.7 or 11.7 ml per second. Okay, then my calculation seems to be somewhere off 72, 0.001. Okay, everyone is getting this, right? This is 1.17, and that means this is 1.17 into 10 power minus 3. That means this should be if the blood pressure is 72 mmHg, 7.0. Oh, okay. I did it with that 7.0. Thanks. Yeah. 7.2, this is 10 power minus 6, then 10 power minus 3, 1.1. Then makes sense. I had it as 7.2. Okay. So bottom line, always, preferred thing is get to standard units and do it. Know what the standard units are, in this case, Pascal, and any conversions you needed, then convert it. And if you have everything, you're not writing things down, GATE calculator won't make a round of approximations. It'll in the worst case, it's going to write, in scientific notation, and it'll keep sufficient digits. Okay. Only if you write things down, you might get into trouble. Any intermediate step, if you write it in a paper, you'll get into trouble. Otherwise, convert to standard units and do the finally get whatever number you want. Okay. This again is a slightly tricky question. Patient's cardiac output was measured by thermodilution, and this suppose aortic valve area is what we want. Okay, this is Q by C from my memory, delta P by 2 rho. Is it P? Is this correct expression correct, or need a slight change?
It's rho by 2p, 2 del p.
Rho by 2 del P. Okay, thanks. So again, let's get the number right now. Let's just do it. Okay. So C is given to be 1, discharge coefficient. If you assume it to be 0.85, something like that, that is fine. Okay. This is C is 1. For now, let's just keep C is 1. And then this is 6.4 liters per minute. Okay. And that is 6.4 into 10 power minus 3 meter cube per minute. Okay, that is 6.4 into 10 power minus 3 meter cube by 60, so per second, meter cube per second. So we know the flow rate. Oh, we have to do convert the cardiac output to, we have to find Q from this, right? Okay, anyway, so this is CO. Okay, so notice cardiac output, take flow, okay, multiply that, the flow in each beat is roughly multiply flow rate by this time, approximately I suppose 0.33 seconds, okay, into 0.33. This is the amount of flow per per beat into number of beats. Okay, so this is the amount of flow per minute. That is by definition cardiac output. Okay, so this, you get this from this figure, approximately 0.33. Okay, from that what is Q, because cardiac output is given. Again, it's a good idea to convert that into meter cube per second. Okay, and this flow rate is in, let's say, meter cube per second, so that you multiply that per second, you get per beat, then you number of beats, you get total flow rate per minute. So what is Q, what is C, rho is given, and then you also know del P. I suppose del P is not given, that you have to find from the figure. Again, it's approximate. Okay, so roughly we want this distance. Okay, presume it's the difference is a constant. This to this. Again, there is one more approximation. The figure needs to be much better. Total is 100. Let's say half of that. So let's say this is 50 mm Hg. Okay, and we presume that that 50 mm to be a constant across all time points. That's the best approximation we can make with given info. So del p is 50 mm Hg. Again, let's convert that to pascals. I suppose 50 into 133 pascals. Okay, so if your del p is given, rho everything is given. So what is the valve area we calculate? 81.9, approximately that, I suppose. Akansha Hema, approximately 100, 10 by 10. So 89 makes sense. Okay, so again, a problem that we have done in class, just that this way of writing things is easier to interpret. Other than that, it's this we get from approximate Bernoulli, and also remember this is an approximate version where we think one of the areas is too large and completely overlook it. They can sometimes cook up this problem so that ventricular area also is finite and you need to account for it. But usually the changes will be like very small. Okay, fine. Let's get to this again. One more problem we have done in GATE many times. Yeah, let's do this for units sake. We have multiple pores. Okay, details about one pore is given. Viscosity is given. Aggregate area of number of pores. So information to find number of pores is given. Pressure change is given. Total available area of nearest value of filtration rate. So this comes from this. P is R Q. Okay, Q1. So filtration rate, it's not per pore, it's just total filtration rate. Okay, Qn. Qn is Q1 into number of pores, n pores. That's it. So notice this is del P is 8000 minus 6200. Okay, that should be 8 μl. 8 into 0.002 Pascal per second into L is 60 into 10 power minus 9 by pi r square. So pi into r is given 1 into 10 power minus 9. So 10 power minus 9, this power 4. Man, this gets way too small. So 10 power minus 36. Okay, this times Q1 times number of pores will be quickly, how do you 5% of the total area. N pores is total area, that is 1.5 into 0.05. Okay, by volume of area of one pore. So pi r square. Okay, suppose couple of things cancel here. Is resistance is 8 μl by pi r square, right? Just correct me, help me with this, pi r power 4, right? Or is it? Then I have Q1 is by number of pores. So yeah, just I'm just wondering, Q1 by n pores. So this is Q1, instead of Q1, just write that as the flow rate we are interested in by n pores. So 1.5 into 0.05 by pi r square. So 10 power minus 18. Yeah, now the numbers kind of make sense. So this thing should get somewhat cancelled here, here. This should become 10 power minus 18 at least. Yeah, then finally find Qn to be, let's get the answer. So this should be in meter cube per second, okay? And then find that answer and then tell me, let's convert that into meter cube per minute. So the flow rate you find from here, what is that? 140.63. Suppose Nandini is that is correct, and then take that 140.63. 1 meter is 100 centimeter. So 10 power 6 per second. Nandini, we have some kind of, it's not this much. See, this problem we have done like 100 times, but still every time we do it, we get some kind of 1.4 seems, 140 seems too less. Okay, thanks. Again, the point is highlight, the actual knowing this and actually doing that. It's suppose 1.4 into 10 power minus 7 meter cube per second. So then things make sense. Into 10 power minus 7 into 10 power 6 centimeter cube per second. So per minute into 60 per minute. So this I suppose is 8.43. Yeah, 1.4 into 10 power minus 7 or 140 into 10 power minus 9, either is 8.43. Yeah, recognize things appear, all the things we know, but this unit conversion gets really, really painful. And let me also draw a line here so that you know where things are coming from. Okay, one more this question, let's also do it. Again, this is, so this question already showed up in GATE. Okay, realize, okay, messy number calculations. Let's also do one more problem like that. Please numerator meter us. This is likely to show up. I'm expecting any year. As 100 capillary tubes, each is the diameter of this and this. Pressure drop that occurs for a flow of 1 liter per second is just pascals. Assume viscosity to be 1.8 into E5 in Pascal seconds. So flow rate, first let's calculate, again the same thing. Q is 1 liter per second. Okay, this is 1 into 10 power minus 3 meter cube per second. This is total. Okay, Q 100. So flow in 1 should be 10 power minus 5 meter cube per second. That's the first thing that we notice. And then, yeah, then things are simple. P is R times Q. So that is, we want P, right? Yeah, directly multiply things. 8 into 8 mu L into Q1 by pi R power 4. Diameter is given, so pi D power 4 into 4. Okay, let me write down things in proper unit. L is 5 into 10 power minus 2. Diameter is 10 power minus 3. And then viscosity Pascal second, that is fine. Newton's works with. Flow rate, we already converted, 10 power minus 5 meter cube per second. If we calculate this, what do we get? 8 into 1.81 into 10 power minus 5 into 5 into 10 power minus 2 into 10 power minus 5 into 4, 0.14 divided 10 power minus 12. Megha is getting a number. Nandini is getting a slightly different number. Yeah, I got 92, which is what I'm also concerned about. At least whatever I have written, I suppose is 92. So 10 power minus 5 into 4 divided 3.14 divided 10 power minus. Sure. Yeah, I did. Yeah, pi d power into 16. So into 4, 92 into 4. 92 into 92.23 into 4. 368 pascals. I put pi d power 4 into power 4. This term was slightly off. I had this as 4. Okay, 368.92. 36.8, no, doesn't make sense. I suppose this is correct. Then this question is a gate question. My answer would be this. Okay, let's also, if you remove this, the cold saline volume is too small. Yeah, I would agree with that. Yeah. This is a slightly somewhat of bad question because it doesn't give us insights, and also this formula is very very specific to a particular thing. Okay, so in the next mock bioinstrumentation, that's why I gave a different question, that is actually give some temperature as a function of time and then calculate things. So this cardiac output measurement, all these coefficients depends on a very very specific formula that has been calibrated for a very particular device. So it's not all that useful to extrapolate to to a different scenario. So instead that I'm going to skip this one problem. We'll certainly come across proper cardiac output measurement, even see some intermediate calculations in a question that follows next. Okay, patient's spirometer O2 consumption was 250 ml per minute along with 0.2 ml per ml arterial O2 content, and this cardiac output is. So CO into this atriovenous difference, this is the total consumption per minute, right? And that difference is 0.2 minus, let me write this as C arterial minus C venous. Okay, this should be the total consumption, O2 consumption, and this is in rate. Okay, so things are fine. Cardiac output should be this O2 consumption, 250 ml per minute by this thing, by 0.2 minus 0.15. So ml per minute, and then from there liters per minute. 250 divided by 5000 ml per minute, so I get 5 liters per minute. Okay, pretty straightforward. Again, the same idea. Okay, one more gate question. Yeah, we have some time, so let's again do this. In the process of measuring blood flow, voltage you say is BLV, and we want the flow rate, right? So we have to, let's say this is B average, is also somewhat approximate. So BL in this case is distance between the electrodes, so that is D. So into 2 times radius is the distance between the electrodes. V average is flow per cross-sectional area, so that is by pi r square. Okay, so diameter is this. So r, say r is 0.25 into 10 power minus 2 meters. Okay, so we have r. Weber per meter square, no, somewhat standard, so you can use things as such, and from here you can calculate flow. So 3.75 into 10 power minus 9 is 1.5 into 10 power minus 5 into 2, this thing get cancels, into q by pi into r, so that is 0.25 into 10 power minus 2. So if you find q quickly, what do you get? 3.75 into 10 power minus 9 divided by get q to be 9.8 into 10 power minus 7 meter cube per second. So that becomes 0.98 centimeter cube per second. Okay, great. Potential generated in electromagnetic flow. See, again, it's the same thing. So what is Weber per meter square? So this is in standard units. This is Tesla, right? This equals 1.5 into 10 power minus 5 Tesla, right? The same thing is given over here. So I suggest you also do this problem using the same means. Average flow rate is given, potential generated in an electromagnetic flow meter. Okay, now E is BLV, and so radius is given. So B into 2R into Q by pi R square. Okay, so that becomes B into TQ by pi R. So now make this in Tesla. So 250 into 10 power minus 4 Tesla, that is Weber per meter square. So we sorted one detail. Then flow rate, put this in meter cube per second. So that is 175 into 10 power minus 6 meter cube per second. And R 0.9 into 10 power minus 2. So if you substitute all this, you should get answer in volts, then do that, remove 10 power minus 6 from that. Let me quickly do this. 250 into 10 power minus 4 into 2 into 175 into 10 power minus 6, 3.14 divided by R, 0.9 minus 2. No, I don't get 310. I have, yeah, 310. 3 into 10 power minus 4 volts. So approximately 310 microvolts. Anyone get the same answer? No. I see. If you just calculate based on the numbers I have put in, okay, I get this to be 3.096 something into 10 power minus 4. So this answers, based on this standard unit should be in volts. So notice that is approximately 309 microvolts. 309 or 310. This is 3.0962. So this 310 is better. Sums and others. I think this book, I think this is from Corin Brown. They will use some kind of formula here directly. This is by 50 QB by 50 pi R, I suppose, something like that. If you plug in things directly as such in that formula, you'll get it. But I suggest, always stick with one thing, plug in standard units, and then, do the final conversion. Formula that work for specific units are not that useful. Okay, PZT crystal thickness, longitudinal pressure wave, Doppler shift. Doppler shift 2V cos theta F over C. So this is C in, there are two things. So let me write this as C tissue, and this F is lambda is 2D. Lambda is D by lambda is D by 2. Okay, so this is C over CF.
So D is lambda by 2.
Yeah, sorry, D is lambda by 2. Lambda is C over F, right? That equals C over 2F. So you also know what this F is. 2V cos theta by C tissue into that F notice is C over 2D. This is C different C. Let's say C PZT by 2 times D. Again, let's put things in proper units. V is 10 power minus 2, 10 into 10 power minus 2 meter per second. And then we have, this is in meter per second, this soft tissue, C tissue. And this is CPZT. We want to find del F. And then thickness is 10 power minus 3 meters. I suppose we know all of that. The angle is 30 degrees. Okay, if we calculate that, what do we get del F to be? 224.9. Okay, fine. 224.9. Okay, pretty standard question, and so combines Doppler shift with something else. So always look for questions like this. In fact, now if I have to complicate this question slightly further, I will make this. I will give capacitance of this or something like that, so that distance right in terms of capacitance and all that. And 830 laser oriented at. In fact, I should have given this question first. Somewhat of a simpler question. Delta F is 2V cos theta F over C. Everything is given, so things are fine. And notice this is laser Doppler flow. Okay, so this is velocity of sound, light, and so this should also be velocity of light, c over lambda. So this lambda is 830 into 10 power minus 9, and then we have b 3 into 10 power minus 2 meter per second, and then 60 degrees, that is fine. And then so you'll get this in hertz, and then convert that into, divide by 1000, you should get kilohertz. That is x.14. This value as such is 36114.5 something something so 1 hertz. That is 36.14. Great. Okay, transit time ultrasound meter. We discussed this. Anyone remember the formula here? So we have a probe here. We have a probe here. Typically, velocity along this thing, and we send in this delta t is calculated. So okay, mean velocity in gaseous medium. Anyone remember? Okay. Delta t c square is 2 u l cos theta, and this l is directly this distance. This is l. Okay, you want c square on that side? C square. So there is one detail you want to be careful about. What is the answer we get here? Others, anyone else? We have two 4.4s. Let me also quickly check this. Cos of 30. I get, so if you just calculate using this expression, I get u to be 0.0445 something meter per second. So that is 4.45 centimeter per second. Okay, so the one detail you want to be careful about is, so what is given here is this L is given, right? They can, typically shows up in two modifications. Okay, This is given to be L. Okay. Sometimes they can give this diameter. And relation between diameter and this thing should be, this angle is theta. This is D. Sometimes D is given. Sometimes D is given. So you can calculate L from D. Okay. So L is L sin theta is D. L sin theta. So D by sin theta. Right. You will have to calculate L from this. Okay. Sometimes they give clock frequency. So there is a measurement device to measure this, transit time that has a resolution. That resolution is given as frequency. Okay, 1 over del T is given. Okay, so this is given as clock frequency. Given as clock frequency. Again, you have to recognize, okay, this is the minimum resolution we can measure. That means 1 over that should be, or 1 over that is given. So delta T is that. You can infer from that. And yeah, typically they slightly complicated. They give it with these two modifications. Then rest of all things are fine. Remember this formula. Remember how to, there's an approximation. Just in case there is a need to find what this transit time is, just speed distance problem. So you could also get that. Okay, roller drag infusion pump is driven by a stepper motor that advances the shaft rollers. This is actually very, very simple setup. All it has is it essentially has like a tube-like thing. Each pulse it kind of presses. Imagine this toothpaste and squeezing the toothpaste. It happens like that, but in a cylindrical geometry. The tube is like this. Okay, and then there is something to squeeze it and roll it. Okay, let's say this is like a wheel that presses the tube and rolls it. Okay, that is one pulse. So what is given here is this geometry of this tube that is given. This speed of this roller, I suppose, is given. So these many number of degrees per step is given. Okay, and this radius of this geometry is given. This radius of this roller is given. And the tube's inner diameter. So tube's inner diameter can calculate the geometry. The idea is roughly in one pulse, it will squeeze, this exaggerated 1.8 degrees of the circumference. Okay. So quickly, circumference of this tube or 1.8 degrees corresponds to some L. We have to find that L. So that is pretty simple. Take this 2 pi r. Okay. Notice L is take 2 pi r. That's the total circumference. Just 1.8 degrees of that. 1.8 by 360 degrees. Okay. This is the length to which it squeezes. Okay. Roughly the amount of drug squeezed in a pulse, almost like let's say beat. Okay. That will be L into A. Cross section area is squeeze per pulse. Okay. Let's quickly calculate this volume. So we know the total amount at which it should squeeze. So if we calculate this, divide this by this, there should be n pulses should lead to this much amount of total rate. So what is, just find LA from here quickly. 2 into 3.14 into radius of this is 4 minus 2 into 1.8 divided by 360. 4 into 9.86 into 10 power minus 9 meter cube per pulse. Okay, that is each pulse is squeezing this many number of this much of volume. So we want 0.5 ml in total. So how many pulses would that correspond to? That is number of pulses per minute. So quickly convert, either this into meter cube or this into meter cube. So 0.5 ml is into 10 power minus 3 liters is 10 power minus 6 meter cube is what we want, and then divide by number of one pulse. You should get number of pulses. Yes, I am getting 50.7 pulses per minute, but I suppose the book answer is somewhat different. I'm wondering where this is. This 360, 180 degrees. I suppose that is fine. Let me just double check this. 2 into 3.14 into circumference we are talking about is 4. Ten power minus 6. 2.46 into 10 power minus 8. Okay, sorry about that. Does this give proper answer? 0.5 divided 0.46. Yeah. 2.46. So that gives roughly 20 pulses. Okay, first let's take a step back and let's understand, if you have questions here, let's get one part at a time. So instead of doing L into, pi r square, I did L into pi r. That is, I just did 2.5. I didn't do 2.5 square. That's why I got some other number here. Okay. So any questions with this problem? So this is, just I gave this because drug delivery is there in biomaterials, and it's another rate type of problem. So, and it's almost like a cardiac output question. So, instead of one, it's like finding the heart rate given cardiac output and stroke volume. What we calculated, the amount of volume squeezed per pulse is this. So that is like stroke volume, and then this is like cardiac output, and this is like heart rate, number of beats per minute. In this case, is number of pulses per minute. If that analogy makes sense, and all you have to find is find the stroke volume from this geometry. We have a we almost have a cylinder wrapped around in a circular fashion. That's it. So take the cylinder, wrap it around a diameter of 4 centimeters. So that is the setup we have here. Other than that, it's just almost a cardiac output type of question. Okay. How much time we have? Some questions, I think once we cross this resistance and all that, I suppose following questions are relatively easy. Let's just hope for that. Anyways, let's do the full calculations properly. Total lung capacity is this. Patient's inspiratory capacity is this. Okay, others, are you getting 20 pulses per minute? Kishore had 50.7 because he was following along these numbers, but others, are you getting 20? Okay. Okay, TLC is given, inspiratory capacity is given, we want FRC. I suppose TLC is inspiratory capacity plus FRC. So FRC should be just difference between the two. 5.9 minus 3.3. 2.6. This is, of course, we just have to recall all this lung volume relations. This is not that tricky, but this problem is slightly interesting. So sometimes you might wonder, how do you measure the total lung capacity, because parts of that is not at all accessible. So what you do is you make a person breathe into a container. Okay, we have the person, say the lungs, his mouth, and then he breathes into a container. Okay, then you start with a known volume. So this is container, so this is a reservoir, and this is lungs. So all this volume should be give us TLC. Okay, this is 2 liters, and we have 10% of inert gas. And this doesn't cross the blood-brain barrier. That is important because, okay, this circuit is closed. It's also closed in the alveoli level. Nothing enters the system. So it is inert, doesn't cross the, enter the circulatory system. So this is like a closed, the container, reservoir, and the lungs are like closed system. End of the period that is sufficient for the container of the reservoir and the lungs to equilibrate. The concentration of the inert gas is measured and found to be 2.7%. So you start with 10%, 10% in 2 liter volume. Okay, that kind of becomes 2.7% in 2 plus whatever this systems, this volume is, reservoir volume is 2, whatever rest is, I suppose, the total lung capacity. So that should be 2 plus TLC. Okay, and so between this, the mass is conserved. Okay, concentration, let's say, is mass per volume or even volume per volume, whatever it is, okay, mass or the corresponding volume is conserved. So concentration times volume should give, if it's in percent, this should give the total volume of the inert gas. Okay, that should be equal to the total volume of the inert gas at the end of this experiment, C2 into V2. Okay, this statement comes from the fact that inert gas volume is conserved. Inert gas volume is consumed. Okay, with that we know what is C1, V1. C1 is 0.1, V1 is 2. This is 2.7 into percent. So 2.7 by 100 into V2 is 2 plus TLC. From this we can find what the TLC is. Quickly, what do we get here? 2.7, 100, and 5.407. Okay, and so this relation comes from this fact that inert gas volume is conserved. And they could also give this as, mass of, instead of, if they give percentages, so we're talking about volumes are conserved. They give actual concentrations, mass is conserved. Again, you should be able to do this. Mass of oxygen gas occupies, what is partial pressure and all that? 6 liter under a partial pressure of 720 or 760 was, I suppose 760 is a normal, right? Okay, 720 mm. If the temperature remains constant, volume of the same mass of gas. Yeah, this is simple application of the ideal gas law. PV is nRT, so PV by T is a constant. Okay, and top of that T is a constant here. So P1 V1 is P2 V2, and I suppose, let's say V1 P1, then P2 is P2 is given, V1 V1. Quickly, yeah, keep things as such. What is V2? 720 into 6 divided by 716. 5.68. Yes. Have two decimals. Okay, it's if you actually, yeah, approximated, it's 5.7. So 5.68 is slightly a better answer. Atmospheric pressure at sea level is 760 mmHg. Partial pressure of oxygen is dash. What is percentage of O2 in air? 21%, right? Okay, so 760 into 21 by 100. So find relevant data. You need to find this percentage. If you use it as 21, you should get that as 159.6. Okay, again, few gate. This question is a gate question. Arterial blood extracted from healthy adult showed an oxygen. Is this? It's fine. So idea is whatever they are asking for, oxygen content. So this is arterial oxygen content. So CaO2 is dissolved plus bound. So I'm going to write that as CbO2 plus CdO2. Both are arterial. Okay, and C bound as yeah, this hemoglobin oxygen saturation 0.95 into 1.34 per gram, ml per gram, and there are like 15 gram per TL. So this will be in ml per TL. Okay, and CdO2 will be dissolved. So per mmHg this much. So per 40, 0.003 into 40 ml per TL. So add these two. We have CaO2 as be careful about the decimals. We should get Yeah, I think 19.1 is incorrect. 19.25 something, 215 something like that is correct. And be careful about.
Sir,
Uh-huh.
sir, you write 0.003 into 40 ml per dl?
Mhm.
It's ml into dl because it's given solubility of oxygen in blood is equal to 0.003 ml per mmHg per dl. So
Mhm.
is in denominator.
No. So this is what they mean as 0.003 ml per mmHg
Per
dl.
dl.
No,
Per
this is not. No, this is not that algebra 1 over. This is per per meter square per second. Like that, it's per mmHg per dl. See, both are in same units. This is in ml per dl. This is in ml per dl.
Okay.
Yeah. See, this is the way to interpret this. See, this is like saying. Let's quickly take acceleration due to gravity. This is 9.8 meter per second square, is it? This is fine, meter per second square. So 1 Newton, how many kilograms per what is this in kilograms? 1 kilo. 1 Newton is, can you quickly convert that into kilograms? I suppose 1 kilogram meter. Again, this is not convenient.
Pascal,
Okay.
sir.
Yeah, in terms of Pascal. So, but the way to interpret it is just says this. DL doesn't go to numerator. Okay. And then okay, blood specimen has a hydrogen ion concentration of 40 nanomoles per liter and PCO2 of 60 mmHg. This question is important. Okay. First of all, answer for this question is very simple. Blood pH is log of hydrogen concentration or negative of log of hydrogen concentration. So this is minus log to the 10 of whatever is concentration is this. Log 1 over H. Yeah, so minus log H plus. Okay, so this is minus log 10. Notice it's hydrogen ion concentration again, so that is H plus, and 40 into 10 power minus 9 moles per liter. So if you do this, 40 into 10 power minus 9 and log answer 7.39. Okay, 7.39. Remember, they once asked what is this normal pH of blood, like that, right? So that kind of questions are possible here. From here, instead of this is just to illustrate how to calculate pH, but is this pH normal? And is this CO2 normal? That is one type of question they can ask. Or they could go one step further. Based on the value of pH and value of CO2, what is the underlying disorder? Is there like ventilation is problematic? There is too much acid created in the system, acid consumed in the system. Okay, carbon dioxide not being removed, or carbon dioxide as getting removed faster. So those kinds of categories are possible. Okay, so physiology questions, just like that, phonocardiogram, what is going on, such questions are possible here. Okay, we'll get back to this, and sometimes specifically look at this acidosis, alkalosis, and then yeah, those two we'll look at it sometime. And assume that a beam of light passes from a layer of glass with refractive index. Okay, this is straightforward. I suppose it's n1 sine theta 1 is n2 sine theta 2, which is sine theta 2. Let's say the second thing is 90 degrees. So we have n2. And okay, at critical thing, this thing becomes n1 sine theta c is n2. So from that, we can find what is theta c is. What do we get here? Again, keep on using the gate calculator. That's also one of the main objectives of this. Anyone? 78.4. Okay, quickly, let's some gate questions. Let's quickly skim through them. Okay, dye concentrations. We have to use this absorbance is epsilon CEL. Okay, we have to use this relation. The ratio of extinction coefficients epsilon by this in this case should be what? Quickly. Okay, very simple questions. And here we have sine theta acceptance angle is root of n1 square minus n2 square, and F4 wave is 2 times acceptance angle. So 2 times sine inverse of n1 square minus n2 square. Okay, so this again we do. Anyone remember the answer here? KPM 2021, sorry, 2020. Okay, so first order systems. So from here, I think things are relatively easy except for one strain recovery questions. Other answers should be straightforward. So biodegradable suture, okay, 1 MPa in 6 weeks, implanted according to this. Sigma naught is original strength, okay, B is -2. Characteristic time is A is 1 week. Original strength of the suture is. So they are asking for what is sigma naught. Everything else is given. Sigma is given, B is given, that is sigma at a particular time is given. It's 1 MPa at 6 weeks. So, and A is in weeks, so it's also given. Ln 6 into -2. What do we get here? 4.58. You have this? Okay, thanks. Stress of 1 MPa was required to this. After an hour in the same stress position, strip exerted 0.75 megapascals. Stress exerted by the aorta in the same stretched position after 5 hours is. Yeah. So they are doing a stress relaxation test. So at the end of the day, they can also ask like, okay, what is the experiment being conducted and so on. So this is stress relaxation. So sigma is sigma naught e power minus t by a. Okay, or t by our thing relaxation time constant tau. So find tau and then find sigma at 5. So we know 0.75 is 1 into e power minus in 1 hour So 1 by tau. This implies tau should be in hours. This is an hour, this is an hour. What do we get for tau? And quickly, once we have tau, then sigma at phi is just 1 e power minus phi by tau. What do we get for tau? This is 3.48 hours. Okay, take ln on both sides, you get that. Once you substitute that, I suppose this should be minus phi divided 3.48 is that. Shift e power answer 0.23238. Get this? 238, I wrote it as 278, sorry. 237. I said something, I wrote something else. Okay. This question, be careful. Okay. Notice they are doing a creep. Actually, they are doing a creep recovery here. So you apply a constant stress, strain varies like this, almost saturated, and then they let it go. Here, minor, careful about terminology. This axis is in terms of time. This value, strain is given to be 0.20% of its length. So this is 0.2. Okay. And we also given some information to say, okay, 50% of it recovered in 1 hour. Okay. So in 1 hour, we have like recovered is 50%. So strain is 50%. So we have, this is from here, it's 1 hour. And we want to find the strain recovered. So strain after 5 hours is different from strain recovered after 5 hours. Okay, just be that careful about that one detail. This, what is shown here is the strain axis, right? This is strain as a function of time. Strain recovered is this part. Say, for example, any part. This is epsilon recovered. Okay, and epsilon recovered is that this total strain epsilon naught minus epsilon. Okay, just be careful about this one detail. Rest should be, things should be fine. So this is epsilon naught minus, again, epsilon naught e power minus t by tau. Okay, from this, what is the time constant? And what is the recovered strain? So what is epsilon naught? Okay, let me leave some intermediate steps here. 0.1 is 0.2 e power minus 1 by tau. This implies tau is something. And then epsilon naught r is 0.2 into 1 minus e power minus t by, and the t we want is r at 5 hours. Okay, minus 5 by tau. I get tau to be 1.44 hours, and based on that, minus pi divided answer. So 0.173. Oh, I put okay, would be 0.194. Yeah, most of the strain is recovered by then. We are like, almost 5 times the time constant or something like that. So that be very careful. This is 0.1937. 0.194 is fine. 0.194. Akansha, I don't know how you get 0.199. Be careful. And just in case they ask the amount of strain, the amount of strain at 5 and so, that answer will be notice 0.2 minus 0.194. So 0.006. This is the amount of strain at 5 hours. Amount of strain recovered is this. Be somewhat careful about that one detail. Okay. I think like how many more questions do we have? 1, 2, 3. Let's just finish this. Okay, some 10 more minutes. Many are straightforward. Let's just finish that. Some of you notice that they should be not decay to 60% because decay to 60% again will be just one of these conditions. So it's decay by 60% is a better term. And this is one example where we have, there are a couple of ways to do it. We have sigma is a times e power, uh, e power bt. So use this to fit. Okay, both a and b are unknowns. A and b are unknowns. Just be careful about that one detail. Let's quickly write down. So the two equations will be 10 days it becomes decreased by 40. Okay, so 40 is a e power 10t. Decreased by 40, perhaps it's actually 60. Okay, and 50 is a e power 20t. So two equations, we can find two unknowns, or get rid of a by just 50 by 60 is this, and so on. And then what we want is decay by 60%. So 40 equals a e power b into t. This is a t we want. So this is t 60%. This is 10b, 10b. Anyone remember the answer for this? let me quickly see. 10 days, 20 days, somewhere, at least 30 days, 30 to 40 days. It's going to take somewhat slightly longer. Many of you look like you're doing right now. See, the way I look at it, okay, you can solve this. Again, you can get rid of this A by dividing this by one of these two, either of these two equations. So suffices to find what is B. That you could do by dividing these two equations, find B. From 40 to 50, it takes 10 days. From 50 to 60, it's a decay. Things are initially fast, then get slower and slower, slightly more than 10 days. So approximately, 15 days is what I'm looking at, but if you solve it, anyone?
12, sir.
No, so yeah, okay, from 50 to 60, it is 12 days, I suppose, right?
Yeah,
Yeah, then the total number of days should be
32, 33.
32, 33 approximately. Fine, that is. Okay, one more question where, the very basic question, nothing big. V is L di by dt. So what V of E is given, this implies I of t is integral V by L, okay, 0 to t plus, whatever the 0 plus I of 0. Initial current and then start integrating. So, and L is just, I suppose, is 2. Okay. So, I of t is I of 0, that is 2 amps plus this integral. So, 0 to t 4 e power minus 3t. So, u of t take care of in this, the positive integral by 2 dt. It is a dummy variable. If you want to call it something else, you can call it. So 2 plus 2 by minus 3 into e power minus 3t from 0 to t. So this equals 2 minus 2 by 3 into if you plug in e power minus 3t minus 1. Yeah, if you want to further simplify this, finally this is 2 minus 2 by 3. 2 minus 2 by 3 is 4 by 3, I suppose. 4 by 3. So answer is 4 by 3 minus, so u of t minus 2 by 3 e power minus 3t, again u of t. So this is the answer. Sometimes the way they can actually give this in the exam is not as a NAT, but they can either ask you to find the value at some point, or they can also choose the correct expression of current. That is it. Okay. And U of t is just a step function. Okay. This problem, simple, okay, RC problem you have done. 2 kilovolt, this used to do this time constant as RC. Quickly, someone tell me this value. Then once you know time constant, 1.9 is voltage across the capacitor is, 2 minus 2 into 1 minus e power minus t by tau. This is the voltage across the capacitor. Okay, quickly, what is the time constant in RC is just 2, is it? Okay, be somewhat careful. 2 into 10 power 3 into 10 power minus 6. 2 rads 2 seconds. Oh, yeah, I suppose the final answer turns out to be that. So once you know tau, you can write this as a function of time, and then we get let tau here. This implies t is 2. I get t is 5.99 seconds. Just give me 1 second. Okay, sorry about that. Okay, this is I think, okay, again, this problem you have done in class. This question looks hard, but once again, see, um, first order systems, the gate wants to kind of complicate you. This is what they are going to give. This is something very, very simple. All you have to do is understand what the question means. This is where you are supposed to see the reading. Out of range. So the range of the display is this. Okay. So this is, let's say, 0 millivolt, and we have 2 millivolt, and we have minus 2 millivolt. That is the range of the thing. So for some reason, the baselines, let's say it's supposed to be at 0. Okay, that went to 10 millivolts. Okay, so okay, say baseline is this. This 0 when there is no excitation. Let's say there is an offset error. In order to see this R way, what is the maximum value of that offset? That is, when there is no signal, somehow it is not showing 0. There is some offset. There is like non-zero offset. What is the maximum value of this offset so that you can still see the entire ECG wave within these two windows? One millivolt. Yeah. So that is say if this you exaggerate this chunk, if ECG wave is this much, R wave is this, you can see that, right? 1 millivolts on the top one, it will be anything above that, it will go out of range, right? So what is going on here is initially it's jumping somewhere else, roughly 5 times this. So it's going somewhere over here, and then it is getting back the baseline, that is the offset value. The offset value better get to 1 millivolt so that you can see a ECG wave with or wave with 1 millivolts. So this should be 1 millivolt so that we can start seeing the entire R wave signal within this small window. And this jump is 10 millivolts, some error there. I suppose the time constant is given, tau is 16 seconds. Notice if you were to leave it, it's essentially it'll go to this 0. Okay, but we can start seeing the entire ECG until it reaches 1 millivolt. So that's the time we are looking at. So 1 millivolt, we should eventually get to that starting from a value of 10 millivolts, and it decays with t by 16. Time constant is 16. So this implies value of the time is this. One way to look at this one is 2 minus 1 millivolts. That's the difference between this depth at one side and the maximum. There's a max allowable offset. Max offset 36.84 seconds. Yeah, roughly 16 seconds. It's a time constant. So 10 becoming somewhere 3.5 is in 60 seconds, and then getting to 1 millivolts, 2 or 3 time constants. Fine. See, these two questions are somewhat important, and we'll have to deal with this theory separately in class. But right now, the idea is you have a pacer at a heart tissue. Okay, whatever kind of pacer is, also applies to electrical muscles and all that. You want to stimulate it. Now, the amount of current you apply determines whether the region gets activated or not. So this is okay. This is pacing duration. This is pacing amplitude. Okay. What we know is that the spacing minimum duration, okay, required for a given amplitude of current. If you plot it, it kind of looks like this. This is this function that is given over here. This is IR by 1 minus e power minus d by tau. Okay. The name for this is Rio base. Okay, Rio base is actually one aspect of that, but if you either look at Rio base or strength duration curve shows up here. The reason this is important is because of a couple of things. You want to, so you decided, okay, my amplitude ID, I fix it. Based on that, you want to know how long should you pace your particular tissue, right? If you pace it for lower amount, tissue won't get stimulated. If you pace it for a higher amount, in this place, likely the tissue will get injured, burnt, or long time inflamed. Okay, and you're also consuming more energy. So you want to kind of like always stay within the boundary of this curve. If you go above this curve, you are wasting energy or you're burning tissue. You don't want that to happen. So they are very much, from this curve is of very practical relevance in EMG, ECG, pacing, defibrillation, many of the things. So here this relation is given. All they want to say is now the relation is given. They want to minimize pacing duration. That's always the case. Say minimizing pacing duration will maximize battery life. One simple thing, while keeping current at 3 times IR. So ID is 3 IR. Okay. And from this, find the pacing duration D. So just do that quickly. Find out what is, what is D. You should be done. and you also given time constant tau and all that. Tau is given, IR will get cancelled, IR and the cell get cancelled. We have to find D, and D equals 0.811 milliseconds. Okay, very briefly, this is a theory, but we'll get back to that and on what this is. This has multiple applications and consequences. I know this curve, so we'll get back to this curve again. 0.8, 0.1. Okay, exponential. So the decimals here will get some kind of error. Okay, one last question. This is one of the first questions we are looking from electrodes. Most biomaterial questions converting mass to moles to, using this molecular weight. This is grams per mole. We can expect one question like that. If not from electrodes, from biomaterials, this is very, very typical. Okay, I think that a radioactivity question, if so many nucleides decay per second, what is the mass that decays per second? Questions like that are possible. Okay, and just one illustrative example here. Let's quickly do. This is current as a function of time is given. So integrating current, we can get the charge. Integrating current, we can get the charge. Okay, let's quickly do this. This is so 100 into 10 power minus 3, that is 0.1, and by minus 10 into e power minus, I suppose the time is given, right? Time is okay, infinity, e power minus t by 10 from 0 to infinity. How many coulombs is this? How many coulombs does this correspond to? So I converted, this is essentially 100 milliamps is 0.1, and then the 10 should go to the top. No, minus 1 by 10. The time constant should be here. So I suppose this is 1 coulombs. Okay, now Ag I suppose becomes Ag plus electron, right? This is in the Ag surface reaction. Okay, so I'm not writing the chemical reaction properly. Just give me 1 second. Yeah, Ag electrode at this electrode, is one thing, this Ag will then combine with, if there is any chlorine in it, it will combine to form AgCl. The point is 1 Ag atom corresponds to 1 AgCl molecule. Okay, and also this also corresponds to 1 Ag atom corresponds to 1 electron. So how many electrons in 1 coulomb of charge? We need one more time constant. So total charge is 1 coulomb. This corresponds to how many electrons? 1 by 1.602 into 10 power minus 19 electrons, I suppose. Can someone confirm this constant quickly? This is this many number of electrons. That's also equal to those many number of Ag atoms, and that also corresponds to those many number of AgCl molecules. Right? This also corresponds to, let me write this over here, 1 by 1.602 into 10 power minus 19 AgCl molecules. Okay, the number of moles here is divide that by 6.023 Avogadro number, 10 power 23 moles of moles of AgCl. 1 mole of AgCl is this. So these many moles will weigh 1 into 143.2 grams. Okay, this reaction is important. Ag just becomes Ag plus. So number of electrons here, number of charges here corresponds to number of Ag atoms, and one Ag atom eventually becomes one AgCl molecule. So find number of electrons from here, those many number of molecules, convert that into moles. So divide that by 6.02 into 10 power 23, and 1 mole is 143. So this many number of moles, how many weight? Just multiply by that. This answer is, and this unit is in gram per mole. So multiplying by mole, you get this. Zero 0.115. Anyone else? Let me also quickly do this. Yeah, I get 1.48 into 10 power minus 3 grams. So we'll have to do 0.0015 grams. Okay. So this comes under the concept of, this is a very, very simple mole concept, just that many times they exploit this, often overlooked number, this Avogadro number, right? So, but at the end of the day, it's a very simple question. So if this is a current as a function of time, find charge by integrating, find the number of electrons in the charge by using the definition of 1 coulomb. Number of electrons also corresponds to number of similar ions, also corresponds to number of AgCl molecules. So find the number of molecules, that by 142, 143.8 should give you this. Okay. Objective right now is, all the relations very well. Be ready to calculate the final numbers. Okay. All the unit conversions, many of you might have noticed, okay, some units get very, very tricky. My approach is very simple. Always go for SI units, okay, and any approximations, numerical approximations, get calculator will take care of that. But in the process, make sure, even if you know the formula, applying that and getting the number, sometimes, you have to do once or twice. Sometimes you miss a, factor here, factor there, or power here, power there. So you need lots of practice for that. So far, we have done 3 subject-wise mock tests.
first one on MI, right? The second one on biomedical instrumentation, right? It has, biomedical instrumentation. And here we have the third one, right? This is intersection between biomedical instrumentation and, non-biomedical subjects. So, and non-core, right? So this is what we are going to discuss today. These questions are relatively, some of these questions are harder compared to, the questions in the first one. And we also have more number of questions in this test. So we'll have to do it in 2 sessions. In the first session, we'll try to cover about, 50 questions or so. Some of the questions we have already seen, so we'll light pass through them. Some of the questions are GATE questions. Again, we'll quickly, fill out the answer and move past them. And questions that are somewhat new or needs explanation, we'll stop and, discuss in detail. Okay, this is one question that we have already seen. So we have, okay, we need CMRR so that each signal 25 microvolt has no more than 1% common mode noise, right? Okay, so quickly, what is SNR at output? And okay, or what is SNR at, what is SNR at output? What is SNR at input? You also noticed CMRR can be written as a ratio of these two, right? So what is this? What is this? SNR at the output, we want, noise to be 1%. Rest of that, we want to be signal. So that signal is, 100 over 1 in the ratio of 100:1. And then SNR in the input, we have the signal is 25 microvolts and common mode noise is 100 millivolts. So this is 25 into 10 power minus 6 by 100 into 10 power minus 3. Okay, and we have space here. Yeah, CMRR, notice, can be written as a ratio of these things, and we want it in, not in decibels, just the ratio. So it will be SNR out by SNR on the input. And what is this? What do we get here? Okay, we get, I suppose, 4 into 10 power 5. So answer here would be 4, okay, into 10 power 5. And if you want to write it in terms of, okay, thanks everyone. So if you want to write it in terms of dB, our CMRR in dB, that is going to be, these are a ratio of amplitudes. So it's 20 log of 4 into 10 power 5 dB, just in case you also want this. Okay. Okay, suppose this is 112 dB. Pretty simple question. As far as you recognize why this is the case, ratio of the gains can also be written this way. So then this is pretty straightforward. And you have to infer this thing. SNR of the output is actually 100 by the way it is phrased. Other than that, this is pretty simple. Okay. Why doesn't it scroll down? Okay, there is a lag. Okay, so we have the second question. Again, a similar question. This has to do with signal averaging. How do we improve signal by averaging the signal? So signal and noise are in the ratio 1:1. Okay, and we want to improve SNR by 10:1. Okay, so by signal remains same, noise, okay, becomes V over root n. Noise kind of improves. Okay, so this is what happens with averaging, and so we want this ratio by V sig by V noise Okay, and noise average, that should be V noise averaged over root 10. This should be 10 over 1. Okay, and initially it's 1 and 1, so it's cancelled. So root n is 100, root n is 10, so n is, we need about 100 samples to do this. Okay, and that corresponds to 10:1 improvement. In terms of decibels, it's 20 dB. In question, they can actually either give 10:1 improvement or give improvement of 20 dB. This is somewhat illustrated in this question. So again, EEG signal system processes 5 microvolt signal in the presence of 100 microvolt random noise level. Processed SNR. Again, we need some kind of processed SNR. This is, we need a question is not well framed yet. So this is signal averaging. Typically, we need to give some kind of number of averages we do. In class, did we do this? Did we pick any specific number here? Let's just say signal averaging. Let's do 100 samples. Okay. So by 100 samples, our signal remains the same. SNR, okay, is 20 log of signals. This thing remains the same. So 5 into 10 power minus 6, and noise thing will become 100 by root 100, and it's not 100, it's 100 into 10 power minus 6 by root 100. Okay, and what would be this decimal quickly? Okay, thanks. Minus 6.02 dB. Okay, and of course, so the question as such is not well phrased. We need this number. It should say the processing is actually signal averaging, and we'll do this many number of signals, and the answer will depend on what 100 is. So this is again, typical question that very, very simple 1 mark that might show up. Resolution of an 8-bit converter. It has 8 bits. So an input signal, so 10 volt is digitized. And we want resolution in millivolts per bit. So quickly, how do we do this? So 8 bits will allow 2 power 8, this many number of levels. So if you want to be slightly precise, it will correspond to 2 power 8 minus 1. N bit will correspond to 2 power n minus 1. And here the resolution, the minimum difference in voltage decipherable will be this 10 volt by whatever we have here. So 2 power 8 minus 1. Okay. And this should, in millivolts, this is 2 power 8 minus 1, 10 divided answer. Suppose this is 39.2 millivolts, and per bit we have this. Okay, another simple question that, just to warm up ADC, what happens is, one more GATE VM 2021 question. VM 2021. So analog simple, okay, we have like 20 megahertz, and from that we generate 1024 samples. So del F in this case is simple, okay, just do 100 m by number of samples. That should give the distance between frequency points, and in this case I suppose it is 97.6. Okay, and yeah, how do we address this? This is essentially a signals and system questions, but kind of apply to bioinstrumentation. But idea is very, very simple. How do we do this? So there are limits on how fast we can sample based on what is the signal content. Yeah, exactly, just this. So Nyquist, okay, it says this is twice maximum frequency, 2 times F max. Okay, so this is F max is 100. So this is in this case 2 times 100. So just sample it at 200 hertz or 200 samples per second. Okay, it's a simple idea. Okay, and remember this, they can slightly make this somewhat interesting by combining this with some kind of Fourier spectrum information. They can give this not as a text but as a figure, and then they can also use properties of convolutions and products. So you have some products of things, what happens in the Fourier spectrum, what happens to the maximum frequency and all that. They can easily play around with it. Somewhere down the line, I have an example, nice illustrative example. Okay, this is from ultrasound just because we are talking about all the sampling rates, this fundamental limits. I also have put this question over here. For a linear transducer array shown here, a frame rate for a scan depth of this, we need 100 lines per frame. Wave speed is this. What is the frame rate? So quickly, one line will take, time taken by one line will be, this is, speed by distance, or this is distance by speed. Okay. So distance will be 2 times scan depth, and speed will be this C, this is SD, okay, scan depth, C, wave speed, C. This is for one line. For one line, we have this, okay. And in terms of given numbers, this will be 2 into 150 into 10 power minus 3 by 1.5 into 10 power minus 3 per microsecond. Okay, so let's write that into per second. So this many number of microseconds, so that is 10 power minus 6 seconds. Okay, this mm, no needs of conversion. So what is this value? Once you know this is for one line, okay, one frame, it says corresponds to 100 lines, right? So the minimum frame rate here would be like this repeated 100 times will be one frame, right? So 100 times t. So t, I suppose, is 200, okay, 1.5 10, so this is 200 microseconds, okay, and for 100 lines that would correspond to microseconds. This is mm per microsecond, so that will go to numerator. See, speed is mm per microsecond, so the microsecond will go to numerator. So this is correct. Okay, so the total number of frames per second would be 100 times t. That in this case is what is the FPS here? We only get the frame time. This is the time taken. 1 over that should be okay. So 100 into 20 into 10 power minus 6 seconds. So frame rate will be 1 over that. Okay, won't that be 200 microseconds? 1.5 is, yeah, everyone says it's 200. Okay, 200 microseconds. So this is 200, thanks about it. So this corresponds to 50 frames per second. Okay, and again, idea is, so this works for kind of like any kind of transducer. Idea is how this resolutions and frequency corresponds to some of the physical limits in the instrumentation. So scan time is this, that means this is how fast you could, you could image. And this question, the thing is, I actually wanted to give a slightly different question here. And this is also very, very MI specific, all the terminology. So let's not discuss this here. We already discussed this in the MI paper. Okay. And I actually wanted to give a MRI question that is more relevant here, that kind of fits in here. I don't know if you remember that there is one of the questions where we have to do a similar frame rate calculation. And last time we discussed the solution, I thought we took some expressions for granted. I wanted to just explain that, but this is not the question. Okay, so this was already discussed in MI. So let's skip this one. Yeah, see, this kind of now fits in over here. So again, the idea is now we have pulse repetition rate, we have Doppler sound. Okay, Doppler shift. Based on that, now can we have some constraints in the system? So quickly, so what are the things that are correct here? Doppler shift is A. A is correct. Okay, and then frame rate is C. It takes a minimum time of C by 2 RM. Okay, 2 RM by C is the time. So minimum frequency is C by 2 RM. Suppose there is one mistake over here. That is one of the equalities, I suppose, is incorrect. Okay, so this this frame rate better be less than whatever we have here. This repetition rate in this case. Okay, so this should be the other way around, right? No, Nyquist says your repetition rate, how fast you do things, should be greater than twice the frequency of things that you're measuring, right? This is what you're measuring. You better repeat things at a higher frequency, right? So this is incorrect. This is correct. This is essentially the relation that we use there, that twice scan depth and all that. Instead of scan depth, we have range here. Yeah. So instead of scan depth, we have range here. T is this, so FR is that. This relation is correct. B is correct. C is not correct. And once you use the correct B, the B should have, sorry, B is correct. C should have been this. Okay, so this is incorrect. Once you use the correct C with AB, this should give D. Okay, C alone has a minor change in sign. Then, yeah, this is to illustrate there are typically, two types of errors. This is the simplest minimum working example that kind of illustrates the difference. For the actual gate questions will be slightly harder. So now we have errors due to, 3 different sources, maximum possible error. All of the errors get added up. Okay, so 1.2 plus 0.8 plus 0.5. Okay. Option D in Q. So let's plug in these things. I can try that right now. Okay. So we have to. What does this not have? This doesn't have both FD and FR, right? So let's eliminate one at a time. Let's eliminate FD. Okay. So FD is this. FD less than FR by 2. Okay. And FD, we know that is once again, there is a lag here. FR by 2, FD, this we know is 2U. It's always issue with these kinds of forms. Equals not proceed with this much amount of lag in the system. We'll have to find a workaround. Okay, so this is 2U C theta F naught. Okay, so we got one relation over here, and then we also know that can we replace FR? Yes, FR can in turn be replaced. So let's use this relation. So notice FR right now is 4U cos theta F naught by C. That is our FR. This lag is slightly bothering me. Just give me 1 second, guys. So this FR is less than C by 2R. I think you have that expression there, C by 2R. Right? So you rewrite this, take F naught to this side, U cos theta, or take Rm to this side, you got D. Fine, Akansha? Okay, so if this lag persists, we'll just find a quick shift, okay? Okay, the maximum possible systemic error. So things can be on either side. So all the errors get added up. So this will be, I suppose, 2.5%. Each of them is a percent. Okay, and it's plus or minus. We always look at everything being, a positive error, everything being a negative error. That's a worst case scenario. And that corresponds to maximum total systemic error. On the other hand, likely error, questions are missing. Okay, on the other hand, okay, this answer here is this. There is something called likely error, right? So some of these can be positive, some of these can be negative. So we look at this thing, 1.2 square plus 0.8 square plus 0.5 square. So root mean square error, just that, we are not looking at mean of something. This error is going to be there, this error is going to be there, this error is going to be there. All of them kind of add up. So we don't divide it by 3. And to make up for, some of them positive, some of them negative, we square and take root. And so if they ask for likely error, that will be this percentage. Quickly, what is this? Wait, just give me 2 minutes. I'll sign off and I'll be back. Okay. It's hard to continue like this. 2 minutes, stay here. Just 2 minutes, I'll sign off. Okay. Yeah, we are discussing DME3 paper, and then there was a small glitch, so we're back at it. Okay, so this, just be careful about it. Sometimes, maximum error, the other names goes by this is limiting error and so on. This is known as likely error, statistical error, percent error, and so on. Okay, so just be careful about that difference. Okay, the pointer and figure consists of rod with 2 reflective markers. Okay, A and B is here. Location of the 2 reflective markers are provided by a camera-based motion capture system. We call the correct expressions. Okay, so we have one answer. Yeah, all the correct expressions would be all of them here. Notice the point of giving this is how do you parameterize a line in 3D that is not going through the origin? Let's say the origin is somewhere over here. We want to parameterize a point passing through, line passing through points A and B. How do you do that? Okay. So that is why I gave this. Perhaps, and this is also closely related to locating markers in 3D. Something very, very simple, just position vectors. Things are very simple here. And if you follow the vector relations, notice RA plus this RBA, the vector from A to B, RBA, that should give us this vector RB, vector addition. So this is correct. So RBA is RB minus RA. And then notice RT is RB plus RTB, that is the vector that connects B to T, right? So this is correct. And then RT, you could also write that as from RB, you move by a distance D along the direction ETB. That is, E is a unit vector corresponding to that. You have R is, R is not a unit vector. E is, that should have been mentioned here to be more precise. Okay, E is E or unit vectors. That is with the standard convention. So not given over here. So E or unit vectors. So D times ETB. So move a distance D along this unit vector. You will end up at T. Same thing, right? This unit vector direction is also same as the line connecting A and B. So move a distance of D along unit vector EBA. So that also works. This also works. So all of them are correct. Okay. And if actual locations of A and B are given as 3D points, RB, RA, you could calculate, all of this. Okay. GATE BM 2020 question. So there's a nice question on Nernst potential. We are expecting more questions on this. Be comfortable with that. The answer here, I suppose, is C. Okay, solutions are available online. So let's skip this for now. Yeah, this is a nice question on Beer-Lambert's law. Spectrophotometer is being calibrated before being used to determine concentration of 4 standards. So at this point, they could ask you 2 questions. One is, does this follow Beer-Lambert's? Yes, it follows. No, it doesn't follow. Cannot be determined. Or something. One other. Filler option that can be given. Or in this case, if a patient was processed and if a patient sample was processed at a percentage transmittance of 35, percentage transmittance is 35. What is the concentration corresponding to that? 79 corresponds to this, 39 corresponds to this, so on. So what does 35 corresponds to? So quickly here, the relation between transmittance and absorbance will slightly help us. Okay, because at the end of the day, things are what is we look at ratio of absorbances, right? If everything else is the same, the length is the same, the molar extinction coefficient the same, ratio of concentrations will be ratio of absorbances. So we need a absorbance 1. Let's also notify absorbance unknown by absorbance known will be epsilon remains the same, L remains the same, and then we have concentration of unknown by epsilon L concentration of known. So if you know the absorbance, you could do that. Okay, and for this to apply, Beer-Lambert should be satisfied. That we have to verify that here. Can we quickly find out what is absorbance for these transmittance? What is the relation between percent transmittance and absorbance? Anyone remember that? So given transmittance percentage T, how do you find A? Yeah, isn't there a factor of a log somewhere? No, percent T. I somehow remember to be this. Okay, can't we not do this using simple ratio and proportion since we have intermittent values? Yes, you are correct. This is just a verification step. As I said, if they are asking for concentration, it means, okay, somewhere it satisfies Beer-Lambert's. At least you should pick data points that are linear. Okay, So for that, it's better to calculate absorbance and see if ratio of absorbance is ratio of concentrations. So quickly, can we have these 4 absorbances, the 4 standards? Yeah. Your log percent T is 2 minus A. Absorbance is 2 minus log percent T. So quickly do this. 2 minus log of 79.4, that is 0.1, and then 2 minus log of 39.8, that is 0.4, and then 2 minus log of 31.6, we have 0.5, and then at last we have 2 minus log of 20, we have 0.69. Okay, quickly see if the ratios are preserved. This by this, AU by CU is a constant. So 0.1 by 2 is 0.05. Okay, for the first thing. 0.4 divided 8 is 0.05. Okay, notice for all the cases, absorbance by concentration is 0.05. First 2 cases, then 0.5 divided 10, yeah, 0.05, and 0.69 divided 14 is also 0.049, approximately 0.05. Idea is, Beer's law is satisfied in this entire range, so you can use any point. Satisfied in this range. Okay, we have to verify this. That can itself be the question. That is why I gave this in the table format. Okay, so what is satisfying? Beer's law. And then once we know Beer's law satisfies, just use any one point and find this. Okay, so we know absorbance by this. So 2 minus log 35, that is absorbance by C, should be equal to 0.05. So from this quickly we can find what is C. Two minus log 35. So C should be this divided by 0.05. I get 9.9.2 in units of other things. So milligram per liter. Somewhere fits in over here between 39 and 31. 2 milligram per liter. Okay. Okay, another simple question on blood count. Just have to be careful about one thing, careful about the units. We already did some of this in the class. So how many of this is a MSQ? How many of this are correct? Okay, Himanshu says A, B, C are correct. Okay, don't know about D for sure. So, okay, so notice, okay, for this given information, if we calculate, MCV should be 90 micrometer cube, B should be, MCH should be 30 picogram, and then C is also correct. The thing is, D is correct for the units given. Okay, that is, one is in DL. If this is in, D is correct for the units given. You will actually get correct MCHC if you use 100 HCB by HCT here. Correct for given units in question. Okay, so because of that, just be careful about about the units. So if you are given ABC, that is well and good, but based on whether this is ML, DL, whatever it is, this expression is going to change. Okay. For example, notice here if you do 100 HEB, I suppose that will be 1500 by 45. Okay. 1500 divided by 45. Actually, you'll get 33%, 33.3%. So let's say this is also correct, but be careful about this. Okay, now we get into flow measurement type of questions. Oxygen consumption measured by spirometer is this. Okay. So only thing is, so this figure kind of illustrates something. So something enters here and gets consumed here, right? And you know, so and then something comes out here. So it's easy to see if you were to draw a line here, you know, you have a arterial sampling here and you have a venous sampling. It can be done anywhere, but let's say not necessarily here, but you have a venous sample, okay, CV. You could easily see why that fixed expression kind of works in this visual. So quickly, this flow rate should be dm by dt by CA minus CV. And dm by dt is 300 ml per minute. We have oxygen blood gas emission as, suppose it's 0.24 ml per ml in the arterial bed and 0.1 ml per ml in the venous blood. Oh, wait, 0.24, 0.24 and 1.8. So just use these things. You should get answer in ml per minute. And convert that into flow rate per minute. 300 by 0.24 minus 0.18. This will be in ml per minute. So into 10 power minus 3 should give you in liters per minute. Okay. Okay. So I suppose answer is 5 liters per minute. Remember to convert this to liters per minute. Okay. This question needs a bit of explanation. Okay, so this FAN2 is molar fraction of nitrogen. Okay, and molar fraction, okay, of anything, that is number of moles, molar fraction of X, you know, gas X is number of moles of that X by total number of moles of all the gases. You know, in air we have oxygen, you know, carbon dioxide, nitrogen, and all that. So fraction of something will be number of moles of that by number of moles of this. Okay, and we could also rewrite this as specifically this n. We can write that, you know, PV is nRT. So your n will be PV into RT. N is PV by RT. Okay, and here we have to be careful about one detail. Just give me 1 second. Okay. So this is, molar fraction of something by definition. Okay. Now what happens is in the spirometer experiment, you give pure oxygen for a person to inhale. The spirometer initially has 0 nitrogen. Okay, we have state 1. Okay, we have spirometer, and then we have lungs. So this has 0 N2. So nitrogen here will be 0. There will be some finite value. Okay, given by, it says it decreased by 0.1. So this is not equal to 0. And then you do this experiment. Okay, this is state 1. It goes to a different state. Now, as you exhale, some of the nitrogen in your lungs will get to spirometer. Okay. Notice at the end of the experiment, the molar fraction of the spirometer is 0.026. So not 0 to be slightly specific. That is here it's said to be 0.026. Okay. And then the lungs, because some of the nitrogen went to the spirometer, the thing in your lung kind of decreased. Okay. It's again not equal to 0, but this decrease is actually given to be 0.1. So here comes, this question has been asked in instrumentation papers, and which is why we want to also understand some of this expressions and also a quick derivation of that. So number of moles of N2, okay, in, let's say, when you start with state 1, that should be equal to number of moles of N2 in state 2. Okay, and we also need some kind of subscript to differentiate lungs and spirometer. Let's say at the lung and then at the spirometer plus number of moles of N2 state 2 at the lungs. Right, whatever here went here and here. This is a simple, conservation of number of moles of nitrogen. Any question with that? Okay. Now, so this we could write in terms of, the molar fraction, pressure, volume, and RT. Okay. So what this happens is, notice, so this, the NX is, X is, nitrogen we are looking at it. Okay. So moles of nitrogen is conserved. This becomes, let me write P by R on the outside. Pressure, it's a, pressure between spirometer and lungs is a constant. Gas constant, it's also a constant. So let's write it that way. We have Fn2, okay, Fn2 at the lungs at state 1 times your, what is left is volume of lungs by temperature of lungs. Okay, this is LHS. That should be equal to, and to be specific, if there is a change in volume of lungs, we also write it as VL of 1 to be, sometimes these volumes can also change. Then this side, again, the P and R are constants. This will be fraction of nitrogen state 2 in the spirometer times volume of spirometer, the second state, by temperature of spirometer. Lungs and temperature spirometer are at different temperatures. One is at body temperature, one is typically at room temperature, which is why you distinguish TL and TS. Okay, minus molar fraction of nitrogen at state 2 in the lungs into volume of lungs at time 2 by temperature of lungs. So this P over R is a constant, and then also we use this, volume of lung also remains a constant, but we can find the volume of lungs from this expression. Okay, yeah, y minus, just plus, sorry. Okay. So take it to this side. Okay, can I switch to host again? Sure. Okay. How do I get it back? Can you make me host? Nisha was trying to enter. I let her in, but I think some other issue from her end. I did notice that, and I let her in. Okay. So okay, great. Now you rewrite this. What we should get is what we are interested in is this total lung volume is essentially VL. Or that also happens to be the functional residual capacity, if that is noted here. This is normal breathing. So your VL should be, okay, TL over TS into this term, fraction of nitrogen in the spirometer in the second case, into volume of spirometer, this, at N, by difference between this and this, Fn2 in the lungs at 1, or minus, okay, Fn2 in the lungs at 2. Yeah, F12 is higher. Okay, so remember this expression. This they have asked in a MSK once. So this is somewhat obfuscated in Webster because Webster starts with this expression shown here. Okay, shown here. It's hard to see, what is, it says molar conservation, but this molar conservation, how does is actually FVL, it's hard to see, just comes from this, molar fraction is number of moles by this, and then we use that gas constant relation for N. We know pressure and R are constant, so we got rid of that. Okay, now it's a matter of mapping what is what. We'll quickly do that from the question. So the change here is given, this decrease. FA corresponds actually the lungs. Okay, so FLN2 1 minus FLN2 at 2. This is change is 0.1. Okay, and then we are given this consumption is molar fraction of N2 in the spirometer at the end of the experiment is given. So what is given over here is actually this term in the numerator, Fn2s. Okay, molar fraction of nitrogen at the end of the experiment. So state 2 in the spirometer. That is 0.026. Then we need few more things. Spirometer temperature is given. So we know Ts is, this is Ts. Okay, TL, so Ts is 303 Kelvin. Lungs is body temperature, so 273 plus 37. So this is 310 Kelvin. Okay, so we know Ts and TL. Only thing now we have to be careful about is what is Vs of 2. What is the volume of the pyrometer in state 2? So this is, notice this, the way this gas constant works. Okay, spirometer at the end of the experiment is totally connected with lungs. So it should be the volume of the spirometer plus volume of the lungs for this relation to make sense. So this should be 5 plus 7. Vs at 1 is just 5, but Vs at 2 should be 5 plus 7, that is 12, okay, for it to make sense. And if you plug in all of that, you should get a simple number here. Did anyone do that calculation? Anyone? Okay, so 3.192 liters. Okay, this is an interesting example. Already questions instrumentation PYQ has actually asked, okay, what is the relation between, you know, lung volume and the other measurements done in this experiment. So I have also shown the proper derivation here. And it's simple. You could derive that in one line if you know what is, how to do this, you know, number of moles of nitrogen conservation. Okay, now this example, yeah, last time we looked at this, it was some kind of a curve fitting. We couldn't really see what was going on. So I wanted to give a nice example where you could see that. Okay, so we have the flow rate is going to be, you know, calories of injected thing, calories of injected, okay, by you know, again, calories measured, let's say, calories measured. Let's do one at a time. Calories injected is simple, okay. Calories injected is you inject 0 degrees Celsius thing, okay, and so specific heat is, you know, I suppose is one. It is one calorie per ml per degree Celsius, right? So 1 calorie is the energy required to raise 1 gram of water through 1 degree Celsius. 1 gram or 1 ml of water. Okay. So we inject 24 ml and the, you know, the energy, this is at a different temperature. So the content here will be, okay, calories injected will be 24 ml, 1 ml into temperature difference is 37 body temperature minus 0 into, you know, specific heat, that is 1 calorie per ml per degree Celsius. So multiply by ml, multiply by total change in temperature, we know total calories. What does this correspond to? And notice, okay, what is this value quickly? 24 into 37, 888. Okay, and this is given. No, there is a heat loss of 0.85. So out of 885, only, you know, there is some efficiency issue. So only 85 into 888 is what is injected. Okay, accounting for heat loss. So this is the denominator. Okay, now the numerator will be this area, we know, this integral C and all that. So quickly, Q is, you know, this K times Q over integral C dt, right? This is a temperature that we measure, and you know, this is K, and Q, this is Q. Okay, can we approximately write what this integral is? What is integral C dt here? Can you repeat what is when we have multiplied by? One is the specific heat, that is, you know, you need the way 1 calorie is defined as amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. 1 gram corresponds to 1 ml of water. So 24 ml rising by 37 degrees Celsius corresponds to energy of 888 calories. Specific, one is specific heat. Okay, so now we found this thing, numerator. How do we find the integral? So this is C of t, that is, just find this integral. Can anyone quickly approximate this integral?
either you could count the number of boxes here, or if I were to do it, I would just do approximately this is a triangle. Find the area of the triangle. No, approximately. So what goes in kind of goes out. Let's say, okay, what is gained here kind of lost there, and then there is this area. If you approximate it as a triangle, we know the height, we know the width, half times height times width. Half into 4 into width would be 1, 2, 3, 4, 5, 5 or 6. Let's do 5 because things are going this way and this way. So this is 10, notice 10 second degree Celsius. And again, so the way this spans out is we have 0.85 into 888, 10 second degree Celsius. And here also we should multiply by specific heat. Okay. So 1 calorie. So this many calories here. This is 1 calorie per ml per degree Celsius. This is specific heat, the same one that we used there. Okay. So notice the units are such that, okay, this calorie will get cancelled with this, and then you have a second here, this degree Celsius will get cancelled. You will get answer in ml per second. So quickly just find this product over here. Not an issue of delay. This is something else. It's like 75 point. Okay, 75.48. Can we quickly find that in ml per second? So can we also find that in liters per minute? And if you're wondering what this is, let me have the specific heat. 4.53. Okay, great. So yeah, here this is more more transparent. You get to see what happens with the total energy you put in. And also if you take this term to right hand side, you could also say why that is the energy, the total energy that you measure, summation of all the small energies that you do. Okay, you could also see that. And yeah, the proper role that rho specific heat plays here. Often this K is they give a couple of terms there based on whatever calibration, but I felt this example is more transparent. Okay, thankfully GATE BM question. Anyone remember the answer for this? Just write it for completion's sake. Okay, this is NAT. Anyone remember the formula for this? I mean, the final answer for this GATE question? We'll just leave it for the completion's sake. PMMC instrument having following specifications. Angular deflection is, okay, 100 microamps will be dash degrees. No one has done this. Okay, thanks. 9.5 degrees. Okay, so we'll come to the theory of this PMMC moving and all that. But the GATE BM solutions are already there, so let's not spend time here. So I'm trying to write minimal things here.
Okay, suppose this is question 9. GATE BM 2021 question again. What is more precise? Actual measurements or thing. Yeah, the actual measurement notice is suppose 2.5, right? Yeah, actual measurement is 2.5 across this point and this point. We have a 2.5 volt. What is being measured as, on a V1 it's this, V2 it's this. What is more accurate? Things get cancelled down here. V1 is more accurate. Okay, and then what is more precise? This is more closely lumped together. V2 is more precise. I suppose B is the correct option. Okay. Anyways, GATE BM question. Let's move. Yeah, from image formation again. So these are basic thing that shows up everywhere. So it's a good idea to be at least aware of this. We discussed this in class. Total number of patients is 100. Total number of patients with biopsy proven cancer is 10. Notice, so biopsy is considered ground truth. So 10 have cancer. Biopsy proven normal tissue is 90. Okay, so 10 don't have cancer, 90 don't have cancer. Of the patients with cancer, number of patients diagnosed by the physician as having cancer is 8. So only 8 out of 10 was diagnosed. The normal patients, number of patients rated by physician as normal is 85. Okay, and what we want is true negative fraction. True negative fraction, and that would be what is the true negative rates here? I did not. Okay, anyone's. So you don't know the theory behind this. Okay, here we have ground truth. Okay, here we have diagnosis classification. Okay, so ground truth, we have cancer, no cancer, cancer, no cancer, and we diagnose things as cancer, no cancer. Okay, so out of this is true negative fraction. Out of the total people who did not have cancer, how many were rated as normal? 85. Right, so this fraction here is TNF. That is totally 90 people don't have cancer. Out of that, 85 were correctly identified. That is no cancer. Cancer, of course, whenever we are talking about disease, the disease cancer is typically the positive case, and normal things are negative case. So if we have to talk about true positive, things will be different. Out of the 10 patients with cancer, only 8 were found. So true positive rate will be 8 over 10. True negative will be 85 over 90. So true positive, here we have TP, that will be TPF is 8 over 10. Okay, you could fill up the other things. Then we have false negatives and false positives and false negatives. We have false positives here, false negatives here, and we have false positives here. You could fill up those things. Okay. So this is things, this is classified as positive, but that is false positive. So this is false positive rate. You could find it here. And this is classified as negative, but that is false. So false negative rate or fraction, we should go up here. This is the simplest, way to split this, and minimal working example. They usually build more parameters on top of this. We discussed this in a class. I also mentioned, they do a parameter overkill, but at least these 4 you should know.